I'm the most bored. Look at this laptop and just make sure it's recording. Yeah. Wait, am I still in the video? Okay, good. I'm not in the video then. No point watching.
We can see like up to your nipples.
Thank you. Huh?
We can see up to your nipples.
Watch some guy trip on that. I'll laugh.
Okay, guys, we're gonna get started. Thank you guys for coming out, showing your support, coming back to this room. Eric had a little speech he prepared for you guys. So.
All right, well, welcome team, alumni, friends, and all the above. I want you to welcome to the design review of the Titan 13. And sadly, this is my last year on this team. And every year, I've had a chance to work with some amazing engineering students. And every year, same consistency. Amazing engineering students, and this year is no different. It's been an absolute pleasure to watch this team grow and develop into the engineers who stand before you. This team has the passion, the gusto, and the power to do anything, and the reason is because they enjoy doing what they do. Our goal every year is to design and build a Formula SAE car, to push the limits of our school's curriculum and to showcase our craftsmanship as race car engineers. Over the next few hours, the team will present their work and to show how they've contributed to this goal. Being part of a legacy means that you inherit this goal from past teams. Year after year, we continuously improve by learning from last year's weaknesses and making them our strengths. A key trait of our design philosophy this year has been setting goals, quantifying them, and reaching them. We really wanted to make sure that every single person had a goal in this team. If there wasn't a goal, then why be there? Understanding the vehicle and the team's constraints and us as engineers' constraints has been a massive consideration when designing this car. The team is proud of their work, and I don't blame them. The work that they've done is really amazing. I'm truly impressed. And I've been here for 4 years, and this has been one of my most memorable times of being an undergraduate. And so because of that, we won't actually be showing the full car render until afterwards. We want you guys to see the whole process and see how each and every individual person contributed to our success. So, without further ado, let's get started. Welcome. As you can see, no peeks. We're just going to wait until the very end to showcase the car.
So here's how the presentation structure will go. We're going to talk about our team constraints first, move on to the score goal, our life cycle goal, and it moves into the tire selection, vehicle dynamics and behavior, aerodynamic design, structural design, and lastly, propulsion design. So a few constraints that we already set prior to this year. We wanted to know that we wanted a hybrid chassis, and the suspension would be the same as Titan 12, and the tires would be the same as last year's too, Goodyear D2704. And a few budgetary constraint items were the Drexler differential, Öhlins TTX25, OZ magnesium 13-inch rims, FC07 engine, and CAS steering rack. So we had a few questions to ask ourselves before we started. So what is a reliable car? Did we design a well-performing car? What metrics did we use to measure vehicle performance? What is iterative design, and why did we choose this?
So, as I mentioned earlier, we've really been sticking with 3 numbers. First number, 1, is last year's reference. So we currently have 1 car that's still in complete existence that we can get data off of and we can test. So, if you guys want to look at this, actually, and pass that behind. So that is pretty much our logbook of every single vehicle test day we've had. And from there, we can start to log vehicle performance. There's lots of different information regarding maintenance, regarding the setup, regarding all sorts of information. Next is we create targets and goals. These targets is what will define the current design. This is what we want to shoot for, and this is what we try to achieve. And then lastly, for right now, is our actual design components. Right now, we kind of have a 3-step process. And once we have these total design components, we have to ask ourselves, did we meet these goals? And throughout the entire presentation, you'll be seeing what our goal was and how we achieved it. And the last step will be physical validation, and the cycle completes all over again. So the first question we had to ask was, what is a reliable car? The famous saying, to place first you must finish, is a really important term phrase in racing, simply because there are so many SAE cars that will break before endurance ends, and they lose 200 some points. So what we wanted to do is have a goal for how long our car had to last. And this goal we decided was 2 years. The reason we chose this number is because our chassis have to be refreshed every 2 years. And realistically, our team has never seen any car last for more than that long. And if you can look through the checklist as well, I believe we've had 14, 15 test sessions. And if we have one competition every month, we're almost at that mark. So currently, we'd say we're going to go to competition once every month for 2 years with 4 acceleration runs, 4 skid pad runs, 22 endurance laps, and 4 autocross laps. We can then break it down into the number of cycles on different criteria. We start with heavy braking, heavy acceleration, a combined loading, and a number of gear shifts. If our car can last these number of cycles, then we know we've created a reliable vehicle. Next, we got to talk about risk management. Simply because our team wanted to have a well-analyzed car, but we didn't want to necessarily have high factors of safety on everything. So for all these structural components, we decided to assign a risk factor to each component. We developed a list of criteria that are weighted based on the team's parameters and what we thought as engineers would be a priority. So as you can see, if it takes longer than 2 weeks to manufacture, it has a weight value of 3. Simply because we know as our school, and they don't teach us machine shop, we're not the best fabricators out there. We know that if a part has to take more than 2 weeks, then it will probably cause a setback or will probably cause some issue in scheduling. So we apply this to every single part, and we use the sprocket mount as an example. And as you can see, all these different criteria eventually will total to a factor of 8. And what this means is that it's a high-risk item. You can see, we can go into more in depth in the midterm design view slides of what each of these criteria mean. And speaking of which, if you would like to look at any supplementary documentation for the car and the team, that's a nice binder full of all the slides, team expectations, and the likes. Again, going back to the sprocket mount, you can clearly see that, again, the sprocket is a rotating component, so therefore it has to be precisely aligned and it has to be concentric. That's a pretty high risk factor. And it requires a pretty fine tolerance. So all these factors add up to a factor of 8. And we total this up for the entire car, and that's how everyone gets their factors of safety. Now let's talk about performance, and that's what really everyone wants to know about, is what are our goals as a team? And for us, we wanted to be a top 15 team. Now, how do you get there? We totaled it up, and we needed total dynamic points of 460 and total static points of 220. From there, we were able to pretty much reduce some reverse math and determine what our times had to be on the track. As you can see in table 5, these are all the target times we have to hit. And the far right column, we'll talk about later in the dynamic slides how we actually achieve these numbers. So now we're going to talk about a really weird topic about weight. So weight is a really robust, weird issue in SAE. Obviously, you want to design as light as possible. That's simply the fact. Newton's second law says that if you go lighter, you will go faster. That's a fact. However, because we have such a long list of constraints and we are a team that only designs for 1 year cycle, we're really limited in terms of what we can actually produce in terms of weight. So we did, again, 3 steps. First step was to document every weight on the car, and every single nut and bolt, component, upright, bearings, oil, fuel, everything, and figure out how much everything weighs and where it's being located. From there, we determined, again, an opportunity cost, and that sets our goal. Once the team finishes their designs and hits their goal, then we can compare it to the goal and see if we met it. So, but I think, again, going back to what Erwin and I are going to talk about later too, is it's not about weight, it's about power to weight. Power to weight is really a driving factor in SAE, simply because there's such a wide range of engines and a wide range of weights and different tire choices that people will go with. So just to show as a comparison, this is a couple of different schools that we've talked to this year and who have given us their power number, and we can see their power to weight. So currently we have a baseline of 0.129 power to weight ratio, and now we got to figure out how to improve it. So going back to what I said earlier, we totaled up everything in the car, and we kind of figured out how much each component weighs. And this is like a rough estimate just for presentation's sake. This is roughly how much each sub-team weighs. And from then on out, we applied an opportunity cost. We had 3 opportunity costs of 0, 1, and 2. Each different component was really just kind of determining and looking at the team how much weight could be realistically shaved. We started opportunity cost at 0. That was applied to a pull rod bowl. Again, it is very light, 0.053 pounds. There's no way we can realistically shave weight off of it, and there's no way we're going to spend time to do it. It is possible, but it's not worth our time. We then move on to an opportunity cost of 1, and that's a 5% weight reduction. And this is an upright tab. Again, it's still a pretty light component, 0.067 pounds. However, yeah, we could shave a little bit of weight off it. It is something that we designed ourselves, and it is something that we can control the variables of. So now we received a weight reduction of 5%. Next, we go into a weight reduction of 2, and that is 10%. And that is applied to much larger components, and components that we felt was worth the time to reduce weight. So an example is last year's upright. You can see that it weighed 1.79 pounds, and that's, it's weight, but we can definitely shave some weight off of it. So we totaled that up for the entire car with literally every single subcomponent, and we get a target weight of 472 pounds. So we'll talk about the final weight at the end of the presentation because I was actually really impressed by it. Now we're going to talk about power.
Let me switch places. Cool. Hi guys, so power. We're going to be sticking with the XIII engine because we have 2 of them, and it's something we've used before and will require very little rear frame changes to incorporate into Titan 13. It flat torque curve for a linear power delivery, and it has potential to make similar power to popular 600cc inline fours such as the CBR 600 and Yamaha R6 engines. And we want to hit a goal of 100 horsepower per liter. So for us, we want to hit at least 68.9 horsepower. 100 horsepower per liter comes from the OEM, goal of a naturally aspirated engine, what they like to achieve out of the factory. We want to achieve that goal even with the restrictor. So on the left, it's kind of hard to see from where you guys are standing, but that's the Titan 12 photograph after we rebuilt the engine. We noticed it only makes like 44 horsepower at the wheels. After taking the engine apart again for the blown head gasket, we've noticed that the cylinder liners are all worn, and something that when we rebuilt the engine last semester, we didn't take into account to be that much of a power loss. We initially thought the dyno without calibration. That wasn't the case. The dyno didn't change any calibration values. The engine just had such worn cylinder lines, even with the new high compression pistons, didn't make the power we wanted to make. So we only made 48 horsepower at the wheels, 48 horse at the crank. Last year also we had an issue with the intake, not passing text. We had to make a new one the night before, and the calibrations were not suited for that intake. So it wasn't running off the comm. This year we plan to mitigate all those issues beforehand, and the parameters on the next slide, go on next slide. The parameters are in bold are things that will be changing. This year we're using the other engine that we used for backup last year as our primary engine. That engine we took apart has almost brand new cylinder liner, cross hatching still intact. We hope to make the same compression values or even more with the new higher compression pistons as stock to get the 73.80 horsepower that Ricardo Waves generated. Also with runner length and exhaust plenum volume, going to be increasing plenum volume for higher manifold pressures, which will be talked to later by Tim. Runner lengths will be shortened to the smallest length it could be. Same with the exhaust. We noticed that with multiple Ricardo Wave graphs, with multiple intake and exhaust configurations, power didn't change all that much. So we chose to go with the lightest option that we could actually package and manufacture. Those will all be explained later. And with calibrations, we are switching back to 91 octane. Our engine is not knock limited. So no matter how much compression you throw at it, we're not going to get knock. That's proven from the stock bike. Stock bike runs on 87 octane too. We don't need to have such a high octane. So with that, we can decrease fuel tank size and decrease overall vehicle weight. So this is what I was talking about. As you can see on the legend of the graph, R is runner length, P is exhaust primary length. You can see the numbers, they're all varying, plus or minus, I think, almost 20 inches. And our dyno graphs look pretty much identical. That's because power output from the engine is mostly dictated by the camshaft and cylinder head geometry. We're not changing either of that this year, so power output is the same. And this is with the same lambda values and intake restrictor. And as you can see, the one we chose with the first option, R6P20, if you look around 4,500 RPM, that has a slight bump in power. I figured that'd be the best course for our engine because we usually struggle in the low line area, and exiting a corner, I don't want the bog to upset the drivers. Next slide. So design, the whole approach of how we're going to design and prove our powertrain design is first we noticed that we have room in the rear frame to increase our final drive. We wanted to increase it the most it could be without changing the rear frame geometry. We increased the final drive ratio, and that increases operating RPM range given the same vehicle speeds. We've taken that data, incorporated it in optimum lap without the use of first gear. You notice that endurance last year or any other event, we downshift the first from second. Sometimes you end up in neutral. We don't want that to happen ever. So we want to have operating RPM range to be high. So that's why final drive increased. So optimum lap was done with just 5 years, 2nd through 6th. And optimum lap resulted in 8,163 RPM. That is our target RPM we calculated intake and exhaust lengths with. And that's what you saw on the previous slide with the dyno graphs. And then after all that's done, dyno testing with consistent lambda and maximum regulatory timing will be done to hopefully generate the same amount of power as Ricardo Wave generated because the engine now is at good operating conditions.
So now once we kind of figure out, okay, this is our target weight, this is our target power, you can kind of start to see where we start to lie in the standings compared to other schools. So this is a pretty good number, pretty close to USC, 0.16. It's not bad. Now I'm going to bring up vehicle dynamics. And also to any alumni or anyone who has a score sheet, feel free to ask questions during the presentation. Even though, yeah, we are kind of crammed time, we always would like your feedback. Please ask questions, raise your hand, and we'll answer them. Or if we don't feel like talking, write them down and we'll look at them afterwards.
So we're talking about what's the point of having vehicle dynamics again? You know, one thing that you've noticed is we've really realized in previous years how important this was, but sometimes it's a bit later in the game. So the goal this year was to kind of have it early on really determine who is going to worry about this, kind of a little bit from each sub team, because we wanted that integration that Sal always talks about to really be there, you know. So with the design constraints, we do have a limit on power and weight because, so Erwin and Eric went over that, right? We on the vehicle dynamics side are taking that as a constraint, but it's not something we can change too much, and we're trying to get the most out of. Suspension kinematics, we didn't want to change any pickup points. That was something that we determined early on because we wanted all of the analysis and testing that we do on the previous car to be very relevant for this car. And we didn't feel like we personally had the best understanding of how everything was going on the previous car. And so we wanted to further do like more analysis and more data collection on that previous car before we made any big moves without really knowing what we were doing. So yeah, next slide. These were all of the constraints that we have for each sub-team, right? As you can see, since we have powertrain's really limited, chassis is really limited, suspension's mostly pickup points are completely limited. A lot of them are on the aero side, so that is why I'm here talking to you right now. We kind of figured out everything that we wanted to get. We are missing torsional rigidity and then our drag coefficient. So torsional rigidity, the reason that we couldn't really get to that one was because there was a lot of analysis that needed to be done on that, like the level of like high level research, you know, because it's not just the chassis, it's not just the frame, it's not just the monocoque, it is the entire system of the car. So that was one of the areas that we kind of struggled with. And then drag coefficient, we kind of realized that the car was making enough power that we were able to meet the goals that we wanted with our current setup. So yeah, so Joe's gonna go over the tires and everything on that sense.
So I'm just going to briefly go over tire loads. So we have 1.2 Gs on acceleration, 1.7 on skid pad, and 2.06 on braking. And I'll be discussing how I came about with those numbers. Next slide. So for acceleration, we're mostly limited by power from the engine. So I grabbed a bunch of new data from Erwin, got our max torque, our efficiency, our change in final drive, and our new weight. And we came up with a theoretical max of 1.2 Gs coming from the engine. It's not necessarily what we're going to hit because of our car geometry, but it's what the car can output. Next slide. Now for braking, we are going to be going at 60 miles an hour for worst case, and the amount of Gs that we generate will be a product of how much downforce we have on the car at the time. So the lift values that I got were from the aerodynamics team, and these are the two numbers that we're going to be working with. Excellent. And for skid pad, how we went about it was just doing a centerline radius, going at a certain speed in which we can generate the maximum amount of lateral G's. So at 1.7 G's, basically that's the maximum amount of G's that we can generate, going at about 23 miles an hour. Excellent. And then this GG diagram represents the grip that we have during a skid pad. So if you look on the green little dots, that's like empirical data of Titan 12 going around a skid pad. And this shows the grip that we have. And that's how I derived my combined loadings and my tire forces at those points. Next.
So for skid pad, that was how we determined a lot of the values that we wanted for aero. This is how we went about it. We got the skid pad time from last year's car and put all these values, saw how close we were to it. And our assumptions were steady state cornering. This shift time was actually for, what's it called? Storage cell, not skid pad. But yeah, I mean constant velocity without slipping. Next. So this was where I kind of came in and did a little bit of my stuff. I got Joey's code for skid pad and I started to integrate air into all of that and vary what are we supposed to be getting. One of the main things that I realized was the car is not going as fast as it should around the skid pad. Hey, there you go. So the car wasn't getting the times that we wanted. And I was like, why is that? So one of the things I decided to do was, if there's all of these variables that we can't control, we need a correction factor. Because let's say you're going around, right, Chris, you're going around that turn, it's steady state cornering, right? Do you really think that you're never going to turn the wheel? Like, no. In real life situation, it's going to come out a little bit, it's going to come in a little bit, and you have to really understand that when you're doing vehicle dynamics. There's limitations to all these models that we do. So that's what this correction factor was for. Want to go to the next slide? So you can see here from the data, this is kind of why we needed that correction factor. So this dotted blue line is the theoretical G's that the car should be getting. Okay, all the blue stuff is lateral acceleration. Red is the speed of the car. I'll explain that in a second. But so this dotted line was according to our fastest time that we've gotten. That is the equivalent if it was steady state. So if you were going steady state, that's the G's that you would be getting, right? This top line is what we should be getting. And you can see that he is getting to points where he's hitting that top maximum G's that we're expecting. But it's hard to keep the car there. And so what that told me was the car's making the right downforce, right? The car's making the downforce, it's sticking. It wouldn't be able to hit those G's if it wasn't. What it came down to was we're not able to maintain that. And what you kind of see is this car speeds up right before it hits the peak every time. So like right here, the car speeds up, peaks, speeds up, peaks. So that was showing that either we were having a situation where the car was going straight a little bit and then kind of cutting in, or another thing that we noticed was the calibration of the car. When you were driving that day, the tune wasn't right, and so it was being jerky. And you were trying to accelerate a little bit, and it would go faster than you wanted. And so what we realized is if we really want to do well in skid pad, we don't need to look at pure downforce anymore. You know, we need to look at the car as a whole, and we need to look at how does it handle. And so that's one of the things that we did notice was an issue with the previous car. We started to figure out calibration, everyone's mastered that kind of stuff. And it did come out smoother, but this is one of the things that we wanted to focus on. We realized that we didn't really need to increase the downforce by that much. So with that, you'll see that I kept, where is it? Oh, the downforce is on this one. For these two times, this is our goal time so that we can get the placings that Eric previously mentioned. One of the things that we really wanted to hit on the head essentially was this correction factor. We wanted our driver to be able to get closer to the theoretical capacity of the car, and therefore the peak isn't too much higher, but the steady state is higher. And so that's what our goal for this year is. What that came down to is, want to go to the next slide? Okay, no, back. So what that came down to was we wanted to keep for aero the lift and drag the same, but we really wanted to play with that center of pressure. We wanted to make sure that was exactly where it should be, because this previous slide was signifying that the car could be oversteering. And it seems that we do have a center of pressure that's slightly far forward, and we think that might be due to the rear portions of the car in simulations not working too well, and actually making less downforce in the back than we anticipated. So yeah, back to Joey.
So with the acceleration model, I worked with Erwin to get powertrain data, and I got our new weight of the car to see how much of a difference in performance that we can get out of it. So first thing I went with, we had a torque curve, horsepower curve that I used as my inputs. And then I asked him about, okay, how about RPM ranges? So previous years, the RPM ranges were not as optimal as it should have been. It was hovering in the mid 8,000s, but we should have been at about 9,500. So with that as my input, there's an equation where I get my torque, translate that through my final drives at the wheel, and then I get an acceleration out of it. And I connect that point, and I have an acceleration value. And that also gives me a velocity. Then that also creates drag on the vehicle as well. So I have this whole system where once you create one increment, it creates another. So as acceleration increases and your velocity picks up, so does your drag. So this whole model accounts for all of that. And then, so once I have my kinematic equations, I can get my velocity, position, and acceleration at any point with respect to the gearing that we're currently at. And so initially I was getting a time that was way too fast. So I thought, what else could I not be accounting for? So then I had audio reaction time because from what Erwin told me, the driver relies on the noise of the sound of the engine in order to switch gears. So from what I saw, it was about 170 milliseconds in which it takes for someone to respond to an audio response. And then also the time it takes for the engine to actually shift gears, which from Erwin is about 200 milliseconds. And for that time, we are not getting any acceleration at all. And from this, I get a total acceleration time with a correction factor to match our best time that we've done. Excellent. And so 4.38 seconds from 2019 was our best time. And the correction factor I added on was 0.735 onto the initial velocity, because in this model, we cannot account for slipping because I physically don't know how to do it. So, and from what you see in the graphs, the velocity shoots straight up because we have so much torque, but it's obviously not what's going to be happening. So I applied this correction factor, reduced that velocity a little bit to get to the time that we got. And then I applied that to the 2020 model that I created to get 4.19 seconds. Excellent. So this is an example here. So on the left, you'll see time 13. So this is going to be our car. Theoretically, we should be hitting 9,500 RPM. And the drop-off is going to be correlated to the velocity that we're at the moment. So there's no skipping points. So on the right will be empirical data from what the car is actually hitting from the data acting. Next slide. And so if you look here, we don't slip, and that's why we accelerate to nearly 38 miles an hour in like less than a second. So even with the correction factor, this is what we're getting. And on the right, the red line is what the driver is actually doing. Next.
So I'm handling the simulations this year. I'm basically verifying their MATLAB models with Optimal Lap and MSC Adams. So basically, we have these like particle models that they've created, but we want to take it one step further and create a fully like a rigid model, and rigid and dynamic model. So I'm working on that, and it's really, really important to have this because we don't have the capability of being able to make multiple cars and derive empirical data and then change stuff. So if we have these models and we can change inputs easily, we have a better idea of how we're actually dynamically acting. So basically, they've been working on their particle models, and I've been verifying each of the particle models against empirical data using the data we got from Titan 12. The improved models again have been developed by them, and it's going to be the basis of our vehicle dynamics for 2020. So I'm basically verifying if Optimum Lap is a viable model because it is a particle model, and it has been lining up pretty well with their particle models, and that's a good sign. The percent error that I used, that I did a model in Optimum Lap before we did Circle Street Out, and the timing was about 6% off, which I think is decently good percent error. And simulation can provide a lot of feedback to the drivers, so that's why we're using that for driver training. So this is like the piece de resistance of vehicle dynamics. We are trying to model it completely so that we have a great idea of like if we're actually going to be meeting the times that we need to get the scores that to make top 15. So I've been working on that, and it's just like very, very exciting. So both Joey and I are going to be working on that through the spring. Thanks. So this is the suspension setup from Titan 12, or for Titan 13, it's the same as Titan 12. That's the initial model in atoms. We're working on changing the suspension geometry right now to make it as accurate as can be. So there are definite changes that are going to be made. Right here, I did simulations in Optimum Lab and MSC Atoms to see if one is if MSC Atoms is one a good representation of what is going on and if it's actually accurate, and if it's more accurate than Optimum Lab, because we have had success with it in the past. So if you look at the simulation for XIII, because this is a particle model, the velocity obviously is changing over steadily over time. There is not going to be any inputs for gear changes where there would be little steps or it's very even. The same thing with the RPM graph. It's not a good representation of the empirical data because it's basically estimating that you're having less gear changes over the elapsed distance than you actually are going to have. So, where in MSC Atoms, you do see these sets. It's much more representative of what is actually going on because it is a dynamic model. It also is much more extensive with the RPM graph of acceleration because it's modeling after like our gearing changes, so it's not. It's actually more representative of the empirical data we got. I also did look at the speed pad. We're looking at speed versus time versus speed, and this makes sense because obviously you're going to be constantly at a constant velocity through a skid pad. You're not going to be changing. Same thing with lateral G's. It should be evening out as you proceed around the track. Skid pad. This is where some issues came in. It's a much more tricky model to do. Definitely we're not going to be starting at 23 miles an hour. That's not going to happen. But this is more of like not including the build up to that constant velocity and that constant lateral G's we're getting. So the max lateral G's that we got for atoms and for Optimum Lab, Optimum Lab seems to be a little bit more accurate right now because the model is not completely fully realized. We got about 15.27%. Same thing with the max speed in atoms. We don't think that we're ever going to reach 67 miles per hour in XIII. Optimum Lab is much more representative of the empirical data, but as we progress through with the model, it should get close. So the potential errors that we have with both softwares, basically most of the stuff with Optimum Lab is due to the simplicity of the model. It uses a constant steady state cornering, and it's a particle model, so it's really not super accurate to what we're looking at like dynamically. With MSC Atoms, any wrong input can throw stuff off like heavily. So we have to really make sure that what we're putting in is correct and that like it's not throwing stuff off completely. It's also an issue of like interpreting data incorrectly. That can be a big issue as well. So the same thing I said before, the coefficients that usually change usually have to do with arrow. They don't, they're not taking into account an optimal lap. They stay the same over the course of the track. And all the kinematics, all the rigid body elements are neglected. With atoms, the assumptions we're making with atoms is that we're going to use the Pacheco model. You can use many different tire models, but we really want it to be incredibly accurate, so we're going to use Pacheco. It uses a quasi-static setup for Excel and braking. So the analysis is made up of hundreds of steady-state analysis or static analysis with like a linear increasing step time. The suspension geometry and compliance matrix for steering is basically like for all of our steering characteristics. They either use steering or suspension geometry or the compliance matrix, which are like incremental movements of the suspension due to forces on the wheel centers. Some they use both because some are better for specific analysis, like suspension geometry is usually used for toe and camber angles, and the compliance matrix is used for like suspension ride rate or aligning for camber compliance.
So one new thing that I decided to do for vehicle dynamics was to create a quarter car model. And so first thing that I had to do was to define the coordinate system. So you have your first mass here, you've got a second mass down here. You have your chassis, you have all of your unsprung mass. So I decided that going downwards is going to be my positive axis. So the next part will be deriving the equations and then defining these key variables. So spring constants, anti-roll bar stiffness, we've got roll gradients, the mass of the unsprung weight and sprung mass, and then determining the roll and pitch gradients based off of those stiffnesses, wheel rates, ride rates, and the roll centers on the front and the rear. And then from that, I can create a model in Simulink, input certain loads, and then get movement from the sprung and unsprung mass, the acceleration, velocity, and position. Next. And so this is a model of what it's going to look like, except for the cornering setup. There will be an additional spring in parallel up here with the anti-roll bar. And those numbers there will be our roll gradients and pitch gradients that I'm going to be using. So this is what it looks like at the end. So this is going to be taking our right corner and assuming that I input my loads here. So this will be positive input and those will be negative. And so on the next slide, I'm going to be showing you the graphs that I got from this. So if you look here, this is going to be a skid pad run for 4.87 seconds. So this is assuming that once we get into the corner, we hold 1.3 Gs steadily throughout the whole time. So as you can see, since I defined going down as positive, you can see that the yellow, which is the sprung mass, it will lean over and move down a little bit. And that's what it's doing. And then once the vibrations go away, you kind of hold that position for that time. And you can see the unsprung mass does the same thing, but instead the unsprung mass rises instead. So you see this response, and then it holds. And once we clear the skid pad and get back into the straightaway, that's what you see on this side, where it all levels out again. And so this will be for the rear, and that will be for the front of the car. Next. And so this will be for braking. This will be pitching. So going at 2 Gs applied for about 0.2 seconds, you can see the front of our car dips down. And then you can see the same effect. The unsprung mass will rise up, and that will be the rear. It's going to be a reverse response, essentially.
So one thing that I decided to work on was really the kinematics of the vehicle. And one of the things that I wanted to further our understanding is we're making a MATLAB model of our kinematics. So modeling a 4-bar linkage in MATLAB is essentially just mapping out each of the individual points and then simulating a spring displacement. So my inputs for my model is in the pickup points, spring displacement, and ride height. So I need to know all these different variables. And then I plug it into all these slider crank conservation equations and maybe crazy thing we learned in kinematics. And then my output is a wheel position. That wheel position gave me lots of information, such as camber. I can see how the car is pitching, and it really just couples really well with Joey's model. I'll kind of talk about later. So this is essentially what Optimum K is doing. That's what we've always done in the past. However, with this, we get much greater control of all of our variables. We're able to look at each and individual angle and what data and what's going on with the car. We can also put it through post-processing as well. We can export the data into MATLAB or Excel or whatever we like. And we can also take these different spring scenarios. You know how I said you input spring displacement? I can input linear potentiometer data and then get the camera angles and the various loads we get through the car in comparing to our theoretical model. So this kind of all ties it all up together with, again, coupling with Joey's model. Joey's model inputs a g-force, all the static vehicle parameters, chugs out spring displacement and shock speeds. Those displacement graphs, I would plug into my kinematic model. From there, I get the camber, I can look at motion ratio, the tire loads, and then eventually get loading scenarios. I think the more important part of this slide is really just saying that we want to take it to the next step, and this is how we're going to do it. We currently have all these load transfer equations all set in stone already, but we want to, again, keep going further and further to fully make our understanding of the car as well as it could be. So, any questions? Now I introduce the, oh, is there a question? Okay, cool. Now introducing the aerodynamics team of Stanson and Yusuf. And please feel free to ask questions. You guys are really quiet right now. There are as many questions as you like up there.
Thus achieving 1.7 Gs as defined by Joey and Nick on our vehicle dynamics team. Additionally, because we're running a new chassis this year, we had to make a new solution that allowed us to mount that device to the chassis. And in doing the development of that, we had the opportunity to make a few improvements along the way. So essentially what is different this year is because we're changing the chassis design, you can see that I examined the rules and the keep out zones to see where I can increase platform area and decrease drag if possible. Additionally, you have to keep in mind that our CP was forward, so achieving the same amount of downforce was not necessary, and we were okay with losing a little bit if I could bring the drag down. So basically what we came up with is the idea of reverting back to a 2-element wing. And in doing so, we would save weight and also save a bunch of drag. And in addition to that, we could increase the length of the MSHD inward because the chassis was getting skinnier.
Question?
Sure.
How much drag did you say?
So the CL over CD ratio, which I'll talk about later, we actually improved it by 33%.
You know the numbers?
I have the numbers, but I don't have them off the top of my head.
One of your slides had it.
Wait, we'll move on. So before coming to those conclusions, I wanted to try a different amount of configurations to see what how I could achieve that goal. So obviously running the 3-element wing by itself, doing a 2-element wing, and then also capitalizing on the excess area we had with the 2-element wing in terms of deleting the CH10, translating and rotating that MSHD. So those parameters are the same for the 3 and 2-element wing initial iterations, and if I adjusted MSHD, then I would include translation and angle of attack rotation. So just to give an idea of how the CFD was conducted, the assumptions were that the air was incompressible. We utilized a K-omega SST turbulence model and simple foam solver, which assumes turbulence steady state. In addition to that, we had a bunch of inputs. So in yellow, you can see what is exactly input into the software. K and omega were calculated using velocity, length, and kinematic viscosity, and then we also got our delta y value through a y plus calculator that y plus equals 1 calculator that I made. So the way that the process flow started was started off with the front wing from last year and got values for it to see how that one did, and then I wanted to see how it changed without the CH10, and then with the MSHD lengthened inward toward the chassis. So those are the first three symbols I ran, and then after that I decided to see if I could capitalize on additional gains by maybe playing around with the MSHD in the rear, because we do have quite a bit of room behind it. And that's a table right there with the 7 iterations. But as it turns out, our best solution was actually to leave it the way it is. Downforce is highest there, and your CL over CD is best over there as well. So essentially, we decided to run with that design. So final solution, wing looks like that. It has 2 elements. It's lengthened to fit the new chassis, and we meet our goal of achieving 25 pounds of downforce at 25 miles per hour. Now, to make this work with the new chassis, we worked together as Nick was talking about chassis design. So he created 2 flat planes for us, so that way we don't have to run any kind of spacer like we did last year. And we utilize a similar method of having staggered bolts, so that way we can pass IAD. As for material selection on the bolts, we still have to figure that out just to make sure that it fails in the way that we need to satisfy the impact attenuator document.
Can you go back one slide?
Sure.
What's that first one for? That MSHD?
Okay, so the first one is the Epler, and then the one in the rear is the MSHD.
Why are you using a traditional form for the first element? So you go with the final one to take away the ground effect and you don't need as much more attack for the second element?
Okay, so the idea was we wanted to save on time for manufacturing, so we kept the tools the same.
So that's actually something that went over with fees here last year, was having the ground effect was always something that we wanted, right? But what we've noticed, this is work from last year. What we noticed was that when the car pushes forward, it always scratches, correct? Our car, with having a lower wing that takes more advantage of ground effect, is more sensitive to a change in pitch. So if you're braking, you're going to lose all your downforce. If you're rolling in any way, you're going to lose downforce. So by bringing up the wing up, you have a more steady car. And yes, you won't have as good of a efficiency, essentially. You will have a more predictable car, in multiple scenarios. So that is one thing. And we are running the same element as we did last year on that front wing. So yes.
Did you guys do different ride height simulations?
We haven't done that yet. That's when we do the full car analysis. So we're doing that with the diffuser as well, because we need to modify the diffuser a little bit for the mold to come off exterior. So yeah. Next one.
So basically where we're at is, sure, we have a decrease in downforce, but we're still meeting our goal. In addition to that, our CP was far forward, so now it's rearward, and now we can adjust it to make sure that our CP is at our CG by playing around with the diffuser and the rear wing. Moving on to structures with Stanton.
So for the structures, I basically reiterated the ribbon spar assembly, and I'm going to be reiterating the mounting system after we have, since we have a finalized chassis and all of that. Essentially, the ribbon spar assembly is to give shape to the wing and to withstand the loading of the aerodynamic forces to avoid tearing apart. So just to talk about the ribbon spar, the ribbon spar is the rib is basically the 2D profile of the wing, and then the spar connects all the ribs within that element to create the whole element, or to create the whole wing as a whole. So you'll see that afterwards. So in the previous year, for the Titan 12, we used aluminum ribs and a honeycomb sandwich panel spars, which you can see on the left. So currently we want to use the aluminum ribs again with carbon tube spars. The reason we picked aluminum was basically, we considered balsa wood and different 3D materials, or 3D printed materials. What it came down to is how we're gonna manufacture, service, and mount it. We didn't want to use balsa wood because we didn't want to have those mounting points on the balsa wood. And then for 3D printed materials, we just didn't want to go through the time manufacturing that many ribs, because the total amount of ribs you would have would be between 24 and 28, depending on usage iteration, because since you got rid of 2 elements on the front wing. So basically, yeah, on the left side we have last year's, and on the right side is what it's going to be looking like this year. So since we're keeping the same material for the ribs, we're pretty much constrained to changing the thickness of the outer profile. So the outer profile would just be that thickness you see right there.
Go too forward.
Yeah.
The one way.
And then for the spar, we have the outer diameter and thickness of the spar. We're going to be outsourcing it from McMaster, so there's a limited amount, and it's based off of OD and then thicknesses. So here we have the first element, the Epler end rib, and then the MSHD end rib, which we saw on Yusuf's slides. So this is what I was referring to for thickness, just this thickness. And then we have these mounting holes, and then these bigger holes will be where the spars will be going through. So I basically wanted to keep the same amount of spars we used last year. So for the Epler end rib, we have 2 spars. So I wanted to bring that spar in the front, because when we're manufacturing, when we're filling out the leading edge, because we're using 2 skins to bond, when we're filling out the leading edge, the epoxy seemed to like seep through. So we wanted to put that front spar in there to limit that amount of seeping, because every time we put it, it would kind of dry and just seep through, and we wouldn't have anything to sand to curve that leading edge. So overall, this is the S1223. This is just an exploded view of how it would look with the mounting points. So based off this spar, the ones off McMaster have a compressive strength of 75,000 PSI. So we wanted to make sure that it wouldn't fail under that loading scenario with a given factor of safety of 1.2. So I took this as a mounting point, and then this distance on whatever length that we ended up finalizing, and then calculated the bending just to make sure I wouldn't fail in compression. So overall, with the reiteration of the ribs, and then usage iteration, we have the removal of the CH10, which saves 0.567 pounds. He removed the mid plates, as you saw, where it connected the MSHD with the CH10, which saves 0.232 pounds. And then the rib geometry change just from SolidWorks. Since you can see it's 28 to 24, 28 being the amount of ribs we had last year, and 24 ribs we have this year. Since we moved the CH10 had 2 ribs in each one, and he removed 2 of them, so that's 4. And then we have the front mounting integration, which with uses, and we have deduction of 1.48. So that adds up to negative 2.559 pounds, which is just a little less than what we were going for. So going on to integrate the system, this is kind of like the process we did last year. As you can see, this is where we would be bonding it. Then it would come out to this, and we'd bond the 2 skins, so the flat part and the bottom part. And then you can't really see it too well, but there's like a big opening in here, which we would fill with our epoxy. So that was based off my decision of the spar being in the front. So essentially, you would just bond these, and then come out to this after it cured, and then we would lay up the wing skins and then bond them on top. So for last year, a big thing that at least I had a problem with was the jig for the ribbon spar assembly. We essentially just used plywood and put L brackets where we would clamp the ribs down and space them out. But we would drill the L brackets in, so it would have to be, we would have to make sure it was aligned just off of our judgment, and then make one for each element that we had. So last year we had 4 elements, and this year we still have 4 elements. So we technically need 4 jigs. So a lot of issues were just a misalignment. I didn't take a picture of it, but last year we were off by like a 1/4 inch, so we had to throw in like 60 washers, like in the front wing. So it just looked really jank. And I don't know if it was my fault or Lee's fault. But basically, that was like a big issue that I had when I came in. And essentially, a big problem was too that we had to make one for each element. So it was just really annoying to have to go through that mounting points, and the chassis got higher. We have to account for that in the new mounting system. So you can go to the next one. So here's the 2 nodes that or the 4 nodes that we're going to be mounting to. and this is it on the current car. So we have the top mount and then the crossbar. So we'll just be working and reiterating those.
So I got to do the nose. What this came down to was we wanted to hit our, where was it, 3-pound goal. And what that meant was, based on everything that they did, I had to make sure that it was basically 0.5 pound less than last year's, so that we could meet that goal for the overall aerodynamic subsystem. So that's the requirement, and the constraints for front bulkhead. I wanted to make sure everything was tangent to the chassis, just aerodynamic reasons, and so it doesn't look like a thing. And then I wanted to maintain the length of 14 inches. So I hate to say this, but what we found was we could go with the standard impact attenuator. There's a lot of driving factors in this. One of the big ones was the deadline for the impact attenuator document was made that it now gets submitted with SES. Then on top of that, SES was pushed forward, right? So we were under a much tighter time constraint this year. And then once I started to look into that more and more, I realized that it was really feasible trying to hit these weight goals with this foam impact attenuator. With that, the new constraint for the nose cone thus became it has to fit the impact attenuator, and it has to be able to shear with less than 1,000 pounds of force. The reason for that was I don't want to actually crush the nose cone. That would cost me a lot of time, and it's something I don't want to do. So if I can prove that it will shear with less than 1,000 pounds of force, then I can put that in the math, and SAE will accept that I don't need to crush it. So, yeah, that's the design. Yeah, that's one on the next slide. That's the picture. So this comes down to, I was looking at the previous 3 years, how much weight can we shave using this design? What it came down to was the foam actually only weighed 1.5 pounds. And you can see based on, these are the previous 3 years, so this would be Nate's year, Joseph's year, and B's year, how much weight we reduced. We were actually able to remove more weight than we anticipated. So we got a 40% weight reduction from last year. And so yeah, we definitely met that weight goal of what we wanted for the entire assembly. For the assembly, I included everything. The nose cone, which was based off of the surface area, and then based off SES, I figured out how much 1 ply of carbon weighs, multiply that by the area and figured it out. And then the foam hardware, I weighed those out like in person. We already had the foam. I weighed it, same with the hardware. So that's what we're expecting it to come out at 2.3 pounds. So, I like that little video. This is how it all integrates together. So first you have to bond everything together, weld on the 4 tabs for the, I don't know what they're called, cam locks, right? And the nose is going to be cam locked over it because we don't need those 4 corners anymore because it's not going to be a structural nose cone. And on top of that, next slide. Previous slide. Oh, no, that's good. So this is how the cam locks actually attach everything. Each cam lock has a maximum strength of 300 pounds in shear. So what we found was multiplying that by 3, I was able to hit that sub 1,000 pounds. Honestly, the nose cone, if it's 2 plies, is going to shear before or break before any of that happens. But this is something that they would have accepted as a failure point. And then, oh yeah, so the actual tabs themselves are just going to be water jetted sheet metal bent. There's little cuts in it, so it bends easier in that direction, and it's somewhat precise. So here's the manufacturing plan. We are currently on these stages, right, trying to get everything ready for crush. We're gonna have to buy 2 foams, water jet 2 plates, crush half of them. One of the reasons that this was also pushed to be as fast as possible is the new rules. Before we just make a steel tube front bulkhead and crush it. Now it has to actually be carbon fiber. It has to be representative of the front of the chassis, and that means it has to be the front of what the chassis would be. And so we were pushing to get the chassis design out so that we can get all of this going with it. And so yeah, that's basically the system we're going. We do realize that we are going to actually have to make the nose cone mold, so might as well go with the impact attenuator, but it's more of a time constraint, and it was lighter in the end. Yeah. Thanks, guys. Questions? That was quick. You guys did.
No for it.
Yeah.
No. Performance on that?
We did not. So last year, V's team, they did analysis on the tip of the nose cone, and when it came down to it, wasn't very important how much it changed it. But we are going to do, in the full car analysis, we're going to see if there's any issues.
This one.
I think forward.
This one.
Forward.
Oh, forward.
This one. I think that node is too high. That's going to generate that. That's going to
So yeah, that's what we were, so we had 2 theories last year. We were saying if you bring it high, you can create lift, or you can feed more into the under tray, right? Which you'll get more downforce in that sense. What we found when they did it, and I'm not going to take credit for what you did, but what Amar found was that the height didn't matter too much. So when we run the full car analysis, we will see in the end, is the full car performing where it should? Yes or no?
I don't think you can put value in last year's team, so I think you should do your own.
No, yeah, when we get the full car, we will see if it happens. And if we see an issue, we'll go back onto it. But we're not going to waste time beforehand. We're just going to do the full car.
I understand that the goal is basically to reduce weight and to make the car more balanced, so you basically kind of decreasing the
Well, I
performance in the
fucking.
front wheel.
Sorry, what was
With
it?
aero, when you add weight, you're helping the car.
How so?
And
With aero, when you add weight, you're helping the car.
that's the help those.
With
He's
aero,
talking as a top level. In general, but you add weight.
When you add weight,
and you're-
you help your car with, in terms of downward performance.
so actually downforce matters, it's a ratio. So you want to get your downforce to weight. No, downforce to weight ratio. If you increase your weight, the effect of your downforce is less. If you get an SAE package and put it on a Formula 1 car, that car is heavier, but the effect of your aero is less.
And lift effects drives. It's a couple of problems.
No, not lift and drag, lift and weight. So you're
Yeah,
saying,
but I'm saying lift effects drive.
I thought you were saying you want more downforce, or more weight, okay. So you want more,
I'm not saying you want more weight, I'm saying that aero, when you add weight, you're increasing performance. And I understand you guys have a goal of decreasing weight, but instead of decreasing the front performance, maybe the goals are too low for I know the G goals that Joey said, maybe those are too low, and maybe increase the front performance. Where's the undertrain?
the undertrain, no, this is all systems, this isn't like full aero. This is, we're going over the integration of the mounting points.
Have you thought about increasing the rear performance instead?
Yeah, so we're going to balance both of those out. The front went down, we're gonna increase the rear and see if we can get it in the right position. The CP was fairly far forward.
And then are you calculating the yaw movement?
We're not doing anything with the arm.
Yaw movement changes everything. Yaw movement is very important. I don't think, did you do a review last year? Mean cruise, it has a huge effect and it's a major, if you don't implement it, it's gonna change. Your value's gonna be completely different than what you see on the race car. Yeah, definitely implement yaw movement.
Yeah, so what I was getting at earlier with the lift and drag, right? Saying we did see, we're saying, okay, the car could perform higher. What it came down to is the car isn't. If we have, like, let's say we go back to any of the years, we're seeing the car should hit 1.9, and it does, but we're not getting the times that we want. So it's not an issue of like the maximum downforce mentality.
Have you seen Stuart's aero package?
Yes.
It's very complicated.
Are we Stuttgart?
Yes, it's extremely complicated.
That's what it comes down to, though. It comes down to, are you going to bite off more than you can chew and do it poorly, or are you going to do what you can and make sure you do everything right? Do you think Stuttgart's having issues with balancing the car? I don't think so. So that's what it comes down to. Is it's an iterative design.
Oh, I think this final is what you said, but you have so much more potential on the front. That's just.
Thank you. We have more questions?
I had another question, but real quick, listening to this, is the full car model gonna be done before this thing is made?
Yes.
Okay, so if there are changes that need to happen, you can. do it before you-
Retract. Full car model as in like aerodynamic model?
Yeah, or whatever you need to figure out if
Yeah,
this
so
nose is actually gonna be
The
good.
nose actually doesn't need to be made for SES anymore. So that's one of the nice things, is it just has to encapsulate that foam. If we can prove that it mounts right, then we can push off the nose until the day before competition. It won't affect like SES submissions at all. So yes, we will be able to run full analysis with the nose before we have to do it, because the crush is actually doing like 3 weeks, 2
Okay.
weeks. So yeah,
So you will have analysis and data to say whether or
for
not
the, yes, for
that
the full car.
nose shape is going to be good before you actually.
Yes.
Okay. And then my other question is, how are you gonna mount it to the front of the chassis?
So yeah, that was one. Want to go back to the slides? There were 4. Sorry, there was a couple pictures. Want to go a little bit more? I guess that's a good picture. Go back. You can see the cam locks on the top. Cam locks, 1 on the top and 2 on the sides. Those attached to the anti-intrusion plate, which attaches to the chassis.
Can you go to that like exploded view thing, that video that you had of it all like coming together?
Okay.
That metal thing?
sorry.
that the foam is on, how is that going to attach the car? Or is that the car?
These are the bolts that would attach to the car. So
Okay.
those 8 bolts that you see, that's like where the bulkhead is. So yeah.
And then you just reach through the chassis.
So the way we did it previously was we bonded it. You'll see in the chassis, I made that a bit easier because we had issues with it last year. We would bond those nuts in, or those bolts in. We would safety wire them per Eric's genius request. And you just slide everything on, and those are just studs that come out of the chassis, and you just put a nut on it. So yeah.
I was gonna ask about the design process for the nose cone, like why it's
So, yeah.
actually, is that a good geometry constraint, why it's so smashed inward?
Smashed inwards,
From the rules, like it looks like it's really forced inward.
like closer to the chassis.
Yeah,
So it's the same 14 inches. This bottom bolt is to fit the actual foam under it. Because we have to fit the foam in there easily without, trying to do the thing.
so the changes to the front wing are the only thing required to get you guys to the goal that you guys?
No, so we're still going through that. We're still going through the full car analysis and all that kind of stuff. We're the one that we have like basically a database of different front wings. That looks like the one that we're going to use right now. We're going to run full car analysis, see exactly where we are, and like kind of like Legos. Swap out the front ones until we find where we want to go, and increase the rear.
Why not the diffuser?
And the diffuser.
Oh,
So I mentioned during stats area, I don't think I made it clear enough, but essentially that was just a starting point. And then we're going to play around with the other 2 devices and then try to get RCP in the right location.
One of the major issues I'm having on my end for full car is I'm running off of the mesh that we made, right? I noticed that there was a couple of issues with the 120% rule, and in correcting those, there's the mesh changed inside of the refinement box, right? And I'm now getting too many ski faces. And so it's being a pain in the ass in that sense. So just getting that analysis to run, and not just like run, but I want to have like high confidence in it. So that's what we're kind of really ruling out for full car analysis. So, yeah. There we go. Oh no, I'm after you.
Okay. I was like,
Alright, to start off with structural components, here we talk about the wheel assembly. Now, the upper suspension's primary function is to support the tire forces while being lightweight and safe. It needs to minimize compliance and be able to translate the forces into the suspension components without hindering the motion range. Now, this year, we're setting a certain amount of constraints. We're going to be using the same picker points as 2019. We're using the same brake rotor position, the same powertrain tulip, and the rims are not changing, so the wheel interface can be the same. This year we set our goal. Yes, question.
Why particular 4 pounds?
So that's something that in the beginning we thought was attainable, and we decided to go for it. In previous years, comparing to like 2017 or previous year, we've noticed that the more recent years have added significant weight to the structural components, and we want to go back to a weight goal of like previous years or better.
Yes, also we talked about this earlier in the slides. Yeah. If you have like one of the QR code things,
just explain it.
Every component was given like a ranking on what percentage you can lose, and so that's the sum of suspension.
Yeah.
It's like these percentage drops in every component.
Okay, so with this year's designs, what are our results? Well, if we compare the structural components from 2019 to the current ones, we see a total loss of 4.43 pounds, which is above our goal. Now, how did we achieve this? To start off our solution, we're going to take a look at the hubs. The hubs, we need to first look at the bearings. The bearings drive the hub dimensions. And so what we decide to look for is if it's better to reduce the hub diameter, or is it better to keep the hub diameter large and reduce the bearing width? Let's create a model of the hub stress under torsion from braking and bending from cornering, and we chose our bearing based on the greatest weight reduction, the availability to us, and also meeting a static safety factor. So in the end, we decided to go with the SKF 61813 bearings. The reason we chose these is because of their lightweight property, the weight loss, the fact that they do give us a high enough static safety factor above 1, which is the recommended, and they help us package our system. And so this is the design solution that we've come up with. In the front, we've reduced the diameter of the hub slightly to accommodate for the bearing. We've changed the bearings, which has also resulted in a new locking collar. In the rear, the hub diameter has not changed. However, the upright design has changed. Now, how do we verify that designs are reasonable and they will not fail? Well, basically,
So to be accurate. So if you're getting a big deflection, then you may want to run like an up-and analysis. Just
our deflection was quite low. It's just the
Okay.
multiplied by a significant.
okay, yeah, just looking at the scale factor looked a little
Sure.
big. So, okay.
Okay, so running the FEA on all of our remaining parts, we can see that all of them meet the minimum factor of safety of 1.5. And now moving on to system integration. One problem that previous years had. Okay. One main problem that previous years had was in the rear uprights, the position of the brake rotor and the design of the tab prevented the bolts easily being installed into the upright, which meant that if you wanted to do any camber adjustment in the rear, you would basically need to take apart the entire assembly to be able to do any adjustments. This year we've made adjustments to the tab, which will allow for easy modification of camber without needing to remove the entire thing. As for the manufacturing plan, you can see in the blue, that's currently what we're working on. We are outsourcing our hubs to our Connect, just because we have a small team here and because we have a sponsorship now. But we will be doing the manufacturing of the uprights in-house, and we do plan to do them 5-axis this year instead of 3-axis. One reason we decided to do that is because in previous years we have noticed that doing 3-axis machining does add weight, and it also can lead to more errors in the manufacturing process. In previous years, parts have dislodged from the jigs, which has caused eccentric bore holes, which can lead to bearing seizing, which is something that we don't want to happen. In addition, another risk with manufacturing is crashing or tool breakage, and one way we're going to be solving that is by using simulators and by having feed optimization. And we also this year decided to create blue books, which you can see from this example. We want manufacturing of the uprights takes a lot of time. It's a 25-hour cycle time, and so we hope to have multiple people helping out manufacturing. And these blue books will help us do that by allowing multiple people to be able to manufacture, as well as preventing errors by having a data log of all the machine statistics to be able to restart if any errors do occur. With 5-axis machining, you do need to take into consideration how you're going to be jigging up the thing, because we do not have access to 5-axis vices. We need to be a little bit more creative. And so this is an example of a pre-production part that we did in the summer. It involves 2 setups as well as a customized jig, which allows it to be on the 5-axis machine. We are going to be updating this because one drawback that we found making the part this year was that removing the support material caused poor surface finishes, and so we're going to be adding dowel pins for that. So just continuation. Yeah.
So I'll be working on the inboard suspension components, specifically both the front and rear rockers, and we'll also be redesigning the front rocker tab as well. Cool. So major requirements of the design is to reduce a total of 0.58 pounds from the inboard suspension. Again, this was found from the setting each part with a goal for how much could be reduced from it and then adding up all of that. Of course, the parts have to be able to withstand worst case loading scenarios. Serviceability, we've had issues in the past, particularly with the tab, putting it on the car. Anybody who's actually worked on the car would know that it is very difficult to put the front rocker tab on, as you would have to deal with the brake lines, and it's just a mess. So that's something I had to look at as well. And then also create parts that can be machined on the CNC. We had some issues with the tab also, since it was welded in the past. We had some issues with that, so the goal is to CNC machine all of our parts. My major constraints are to maintain the motion ratios, and since our pickup points are not changing as well, that'll be another control. So for the weight goal, my main design solutions, the rockers are going to be, yeah.
Were the tabs steel last year?
They were steel. Yeah, in fact, I think we're actually going to be making them out of titanium, which I'll get to in just a second. So the rockers themselves are going to consist of 2 separate plates, and they're going to have multiple cutouts on them, and then the tabs are going to be machined out of titanium instead of aluminum or steel. As you can see below, I have also made a thing where I said the goal weight of the specific part along with their actual weight, and so we did actually manage to well exceed our total weight savings on the inboard suspension. This is including the rockers, the tabs. Also, we did some weight savings on the bearings and a few other small components in there. So that all sums up to this 0.63 pounds savings. For the serviceability goal, I created a cutout on the base of the tab to allow that for ease of mounting to the chassis. I also made sure that in my design there was plenty of space so we could actually fit a wrench in there to mount it on. And the rocker bearings were chosen so that they are wide enough so they can mount between both rocker faces. So like I said, since we have 2 separate faces, they'll be connected over top of the bearings themselves. As far as part strength, the plate thicknesses were chosen. I did some hand calculations between the points where the damper and the push rod or pull rod connect to the rockers, basically, as that's where the highest stress concentrations appear. So I did some calculations there to see basically what thickness would be required such that the part would not buckle in on itself, since it's only 2 plates instead of a solid part this year. For both the rocker plates and the tab, we did exceed our factor of safety. In fact, on the rear, I well exceeded it, so I'll probably be doing some more material removal on that, since it is very overbuilt. Project risk that I expect to see, in fact that we have already seen, is the shear failure of the tab. In the last month or 2, we saw the front tabs, both of them, the bottom plate completely sheared off, and we had to re-weld them to put them back on the car. It was terrible and terrifying. So this year, to fix that, we're hoping to CNC mill it instead of welding, so that we don't have to deal with any changes in structural ability of the material due to welding, and then also make it out of titanium so that it has a higher strength than the steel did. We also had previous issues with the plates on the rockers bending in towards their connection points over top of whatever they were. That was done due to either very thin plate thickness, particularly on the back, on the rear rockers. We're very, very thin on the wings. So that'll be slightly thicker this year, and then also shim the assembly a little better. That way there's less space for them to be allowed to collapse in. Also, possible risk of doing 2 separate rockers, or 2 separate faces for the rockers, is that the bearing faces, if they're not concentric, that could cause a lot of issues with bearing seizure, and then nobody's happy. So to fix that, the goal is to machine them both during a single operation. That way we can basically guarantee that the faces will be concentric.
How are you going to measure that?
How am I going to measure that they're concentric?
Yes. Are you going to measure it?
It's a really great question.
Previously?
I have not measured it previously, because right now I'm sorry?
How do you know the non-concentric?
Well, so that right now the rockers are made with a single hole. So it's a single piece with a single hole in it, so there's no issue with concentricity because it's one hole. An issue that could be seen by having two separate faces with two separate holes in it is that if I machine this one in one operation and my offset ends up being one number to get to the right diameter for pressing the bearing in, and then I machine the other one separately, and I get a different number to get the right diameter to press the bearing in, they could be slightly offset. Or if my setup for the process is slightly offset, even by.
Well, you can have tool deviation as well. So just because you machine them together doesn't mean they can be concentric.
But more so than if I machine them in separate operations. So that was just my current. Do you have?
Well, I would just say distribution measurement.
Yeah. I will figure that out. I don't know how to do that. I guess we could use. I don't know, but I will look into that. So for the front rockers, I did do some answers. Basically, I started with my hand calculations, and I found my max load at the bearings and the mounting points for the rocker. I applied that, mounted it at the base, did a mesh on it, and then I found my von Mises stress. Essentially, I found my highest stresses to be around 66,000 at all four at the base right there. The strength of the titanium that I'll be using is 123,000 KSI. So this is well below that, which is what gave us our factor of safety of almost 2 on this part. And so I believe that my part is going to withstand all the forces that will be put onto it. For the front rockers, since they're two separate faces, as shown here, this is one of the faces. So when I put the loads onto it, I divided them in half, essentially, since it's a double shear mount. All of the loads that I calculated as our maximum were put in half, and then I put them in their X and Y components, and then calculated that. So our maximum stresses on this one came up to 24.8 KSI, and only in one spot, and again, that's well below the strength of the material. This was our part with almost a factor of safety of 3. So this one's also pretty good, I guess, for the max strengths that are put on. And then here's our front assembly. So you can see the rocker tab there where I did the cutouts on the base, so that'll allow for ease of mounting. And then the bearing and the bearing will be pressed between the two faces of the rocker plates as the main mounting point between them there. So then I moved on to the rear assembly. I did the same thing as I did on the front rocker. I just applied all of my forces in their X and Y components, and then went ahead there. Our max there is 15.7, which is even lower than what was seen on the front rocker, which is to be expected. And so, yeah, all of my parts had a deflection of less than 4 thou, so very, very small deflection on them. And I'm pretty happy with that. So this is the rear assembly. Same as the front. The two faces are being pressed together over top of the bearing. Yeah. So as far as integration, like I said, the rockers consist of the two plates. They're being pressed over the bearings. And then bolted across the other connection points. The rocker tab, I did add that slot at the base so it can be mounted and removed easier without bothering the brake line. Otherwise, it's relatively the same as last year's design. It's just that it's been changed in such a way that it can be machined instead of welded together from plates. Yeah.
What's the radius on the side?
I don't remember, but I did choose it keeping in mind the diameter of a tool that I would be using.
Or you can machine this here.
That's the goal.
How deep is that pocket? The inside one that David was talking about.
On the bottom there?
Yeah.
An inch, just over an inch.
And what size radius were you gonna use?
I believe I have a 1/4 inch in there right now, so that'll be a 0.125 radius. 1/4 inch tool, I mean. I was also planning to do it on a 5-axis essentially, so that I could mill it out from both sides.
Okay. I know that I don't let me speak for David, or else actually machines or stuff. But I do know there is a rule of that. There's a certain tool diameter ratio to pocket depth that you can do.
Okay.
So if you do it from both sides, then you might be able to do that. But,
right. So then my current manufacturing plan for the rockets themselves, since the plates are being machined together in one operation as a way of helping with that concentricity, essentially I'll be machining them out in what's called window frame. So the top of the part will be milled out to shape, and then at the end, I'll mill out that very, very bottom there. So those tabs that are still connecting it to the stock material are, I believe they'd be about 10 thou or less thick, just thick enough to hold the weight of the part. And then at the end, I can cut them off with cutters and then grind down the pieces that are left on there. So fairly simple there. And then the tab itself, as I said, would be machined on a 5-axis. That way I won't have to do 15 different operations, flipping it around to get all the different holes and cutouts on it. As far as putting things together, like I said, since I'm going to be pressing the bearings into both rockers at the same time, this jig is just basically used to keep them in alignment. So that way we don't have any, because if the rockers aren't perfectly parallel to each other in their faces, that'll cause a lot of issues, could cause bearings to do that sort of a thing. So this just basically keeps them in alignment rotationally while we're pressing the bearings into them. And then finally, just my overall manufacturing plan. I'm going to start with the tab, since I believe that'll be probably my most difficult thing to manufacture. And then I'll machine both plates, press in my bearings, and assemble the rockers as a whole, put them on the chassis, and then we're good to go. So that's all I got today. Ergonomics. Unless everybody has questions.
So here for the design solution, this is a 95th model into the current chassis design. And here we can see the thigh angle is 19 degrees with a knee angle of 150 degrees. And the degree of elbow flexion is 145 degrees. And through mil-spec data, we can get close to the maximum output force. So how did I meet those objectives and constraints? I utilized anthropomorphic data to find the optimal angles, and I tested the comfort of position through the trial and error, and also improved visibility through the chassis design, which will be talked about later. So what I'm creating this year is just the seat, and my material selection is using TAP X30, and the process is buy the X30 and then create wood inserts for the drivers. And then once we have the X30, we'll have the driver sit in the car with the inserts and create a gap between his or her back with the firewall, so the bum can go in all the way and create a secure seat. And then after that, we'll cut and trim it and upholster it. And after that is complete. So some of the risks. The risks will only happen when they're driving. So it's either bruising or fatigue. And how we can mitigate that is reiterative seat designs, or have foam or pad inserts for the driver.
So for the driver cell geometry, that's something that's going to be changing this year from previous years. Things that are just some standard things for it are it needs to house front suspension, the front aero, various powertrain components, and a couple of other things. It needs to be comfortable with some adequate visibility, lightweight and importantly stiff, and it's also going to be made out of carbon fiber, so therefore has a stricter SES. So, little preface before all of this. This is strictly the geometry. If you look at any sort of kind of part, it's broken up into two different things. You have your geometric properties and you have your weight properties as of your material. So this basically is just going to be all geometry. That's all we're going to be focusing on here. In the SES slides of everything, that would be focused more so on hitting the material goal of that and hitting that for FSAE and those requirements and everything. With that being said, we want to reduce the surface area by 0.25 meters squared. We want to be able to design a lightweight chassis that helps maintain the power to weight ratio. It's been updated recently, but this was the other one that we had in the beginning. We want a chassis sniffness to be 2,000 meters per degree, and the steering wheel has to be at least 75 millimeters from driver's legs for comfortability.
Why 2,000 newton meters per degree?
Through its research, from a couple of other schools, papers, and looking at other things from FSAE judges and everything, 2,000 newton meters per degree seems like an adequate number to reach for our chassis to help suspension give suspension the accurate numbers they need to read in order for the torsion step.
Did your suspension team do any looking into that? About what a potential torsion spring between your front and rear suspension can do to your setup?
Not necessarily, or a little bit. The thing is, a lot of this testing and everything, it's hard to do prior and like theoretical. I've tried a lot over these past couple of months, and I got a tiny bit of it, but it's a big behemoth in itself. So we're going to rely a lot on the physical testing once the chassis has been made and perform a torsion test on that. Along with those goals mentioned previously before, we would like to have 4 degrees of visibility from the line of sight and oblique planes, additional aero mounting locations, and we will now have this driver cell will now have an access panel, which is something that we have not seen before here at Cal State Fullerton, and moving forward of the anti-submarine feature, which is that slant transition from one height to the next.
So one of the first things that we did was, so this would be like what 4 degrees would be, right? This current, like, it looks like a hockey player, honestly. Where he's currently configured isn't where the driver would ideally be at. This is somebody like 6'1", 220 pounds, but I wish I could have cut you actually. What you'll notice is for the driver, this right here is going to be 6 degrees. That is what we want the driver to see down. If they're sitting down, they want to be able to see this point and this point as one line per se. And that will give us the 6 degrees visibility that we want. So we were able to achieve that, keeping this top the same. One of the main things that we did for this chassis was keeping an inner design. We couldn't change the bottom suspension. So that's like this thing like looks a lot like the previous car, you know. So most of the emphasis was on the top right here, on this side, and you'll see in a bit what we did front too. But yeah, so this one we tried to keep the 6 degree angle, and we found that when the driver is seated, not with his butt here, as was, or the old one was about here, originally intended, but pulled back, they were able to see that. The next slide. And so this comes down to the inside of the cockpit view. So you'll see right here behind it, it kind of just drops off. That's because the camera is made it so that its head would be where that tangent plane is, right? So you can get that 6 degrees view. One of the things that we were sad to do was have to put the Motec right there, but the Motec's also the data acquisition system, so it has to be on the center of the car. You can't put it left or right, or else accelerometers don't work properly. This, though, can be shifted up and down upon manufacturing. We want to actually sit the driver in the car and see at what height is the lowest we can get by with, so that they can see as much forward as possible. We chamfered both of these edges so that we can see forward. We're hoping that if we move when the driver's in, that they can see the end plates, right, where the front wing, so that they can see if they actually hit it coming on, not just hear a thump and then look to the left, it's gone. And then also with these chamfers, you'll see right here, these planes, there's like a little bit of weird stuff right there. The reason that is because all of these planes are perpendicular to the plane next to it. So when you're putting core inside of it and all that kind of stuff, it will actually like lay up. You don't have to do very odd chamfers to get all of that happening.
Say that again?
Go back. So see this plane right here?
Yes.
The plane for the chamfer on this side is perpendicular to it. So the core can actually fit in.
So it's a 90-degree butt, is what you're saying? Or
so yeah, right here, this edge is going to be 90 degrees. And this face right here is going to be 90 degrees. Right here, you're going to get a little bit different. Like it's going to, because if one's 90 degree like this and one's like this, they're not going to match up. On this face and this face will not have a clean connection. So you either have to have all of this at a very sharp angle, or you have to put like a transitional layer here. And the reason for that is when you chamfer the corner and put force plates. You know what I'm saying?
So I'm confused. So are you doing a 90-degree butt, or is it like a?
Are you saying between these 2 points?
I'm confused about your picture and what you're trying to do.
So right here,
yes,
this is all 90 degrees. That's the goal. I wanted to keep all of these surfaces 90 degrees.
90 degrees to what?
To the surface next to it. So this surface and this surface are 90 degrees.
Okay.
So the chamfer or the face that would be right here is 90 degrees to this. And on the right side is also 90 degrees to that. That way when we put all the core in, you can just cut the core and slide it in. See what I'm saying? So that was the goal for all 4. And then on these corners, there's like a little transitional layer so that you can put core splice there and a little bit of core and it'll fill up to where it should be.
So is it okay to do a 90-degree butt joint like that?
On these parts?
On core?
What do you mean?
Is it okay to just do core on top of core like that with?
So
that
this
degree like that?
wouldn't be core on top of core. This would be the determination edge of the core. So the core, do you see what I'm saying? No. let's get a marker real quick.
Let's go.
Okay, so let's say this is like the side of the chassis. Okay, this is the mold. Right?
Okay.
This here, we try to make it 90 degrees.
Okay.
Instead of doing it like this here. Because in the core, when you put the core in, you would have to chamfer this, correct?
Did we really do that?
What?
Chamfer on the right, is that
So
the current
that's
situation?
what?
Is that the current situation on the right?
No, so it's not the current situation, but adding the chamfers would induce that situation.
Okay.
And so the chamfers have to be, these surfaces have to be modified so that this remains a constant.
Okay.
So yeah, it's the way that the old chassis was cut. Since this plane, when you're coming from the right, you're cutting onto a flat surface, that already happens. But on creating chamfers and adding more complex geometry in these corners, that like trait goes away. So yeah, that's what I'm getting at, is these have to be modified from like previous iterations of this for that to happen. That was kept in mind for manufacturing purposes. So yeah, next one. So this was the most frustrating one. Previous years, so last year we mounted right there on the chassis, right? We installed two, what are they called? What was the material? What was that?
Like that.
Yeah, Darwin little like spacers, right? We had issues with all of that, like getting misaligned, and whenever we like the car over the year, I guess not years, all that started to get misaligned more and more. And when you were trying to bolt the chassis in, sometimes it would pop out, and having to rebond everything in now made the alignment between the mounting system and that completely incorrect, and the wing would be misaligned. So this face to this face, the max difference, it was somewhere in millimeters. I want to say like 3 millimeters, right? And then we put about a 4 to 5 inch radius, 2 of them, like this. So we can cut it, slide it in, and core splice around it. Those would both be hard pointed. The goal was that you could put a hard point in there, right? Drill it out, everything CNC precision, and the front wing will be hopefully where we want it to be, and we don't have to worry about mounting, like having issues with its height, angles in every direction, and whatnot. So that was supposed to be a large ease of life thing, and those planes are both flat. So you can just slide mounts up directly to the chassis, bolt into the chassis, and you're good to go.
So what's that depth?
It's not a depth, it's an extrusion.
What's
It's
the
about,
extrusion?
it's like 2 millimeters or something like that.
So have a 4 to 5 inch radius?
Yeah,
And
about that.
what's
So these radii are 4 to 5 inches, and then there's the part line would be right here. So that's why this is fairly high on the chassis, and you have these weird draft angles, so that everything can slide apart.
And your plan is to core splice all around there?
So we're hoping, because we're using the Nomex, the 3/4, that it will be able to deviate, 2 millimeters, which I don't even know that's in inches, but a fairly small amount. If not, we're going to cut it and then shift it down, core splice around it.
So you're gonna fill that whole radius with core splice?
Yeah,
All the 2
you're going to, let's draw a picture. Where's eraser? Sweet, thanks. So you're gonna come from the side, right? Let's say this is the tool surface, which is gonna be, it's gonna come curved right here. This is almost tangent right here, right? And it comes down like this. This right here is about 2 millimeters. Someone tell me what that is in inches. On my phone really quick. What was that? 70 thou. 70 thou, yeah. 70 thou. Thank you. And then these fillets, the reason that it looks big is because these are huge radii. That's why in this corner it gets smaller, because that's the point at which it's almost tangent. And then this just smooths out like this. It's a large radius, right? The goal is that the core will be able to go into this without having too many issues, because we spread out this elevation change over a large area, right? Worst case scenario, we're going to have core come in right here like this, and then core right here, and then just core splice between.
And your hard point goes where it's located?
Yeah, so it's just hard point to go somewhere there.
How thick is your laminate per hour approximately?
And for that, you're using like 3/4 core. I think it was like 0.9 inches in total.
Front line, skin line.
Oh, skin ply?
Your first layer's perfect, how thick is that?
It was 3/4, right?
Yeah, it's 3.3.
30
It was 1 millimeter.
How thick?
1 millimeter.
It's a 343 with the old apartments. So yeah. Anything else?
You got another question over here?
Yeah.
Why is it so big? Like
Surface area wise?
area wise.
So this top spot has to be here. So the chassis parts at this line right here, right? And I wanted this to not be that high because the wing actually will cut, it used to mount around here, right? So I made it extend higher so that it would get into this part line so you can actually remove the mold. But at the same time, I had to keep angles like this so the draft would all work out. And it just came out to be like that.
It looks like it goes down pretty far too. Maybe it's just like
So that's the fillets, because the fillets were very large so that they would make it as gradual as possible. So like probably like here to here, this is all like flat, and then this is all like transitional. So, yeah.
Can you give me like a rough dimension of how this is, like approximately? Is it like 4 inches, or is this like
4 inches, 4 by, I think it was like 3. So if I made this was the shape that I made it, kind of like that, right? Part line coming in here. I want to say this was, these were both. I think this one might have been around 4 to 5, and this was around 3. I want to say inches. So yeah.
okay, so that's gonna show up on your phone faster, right?
Yes.
And you're gonna have to sand that a couple times to get that down, right? And you're gonna have to maintain that feature, the features on that feature, which are your fillets and your extrusion as you're sanding.
So the fillets we're not too worried about. It's just the planarity of that face. So like, well, yeah, the more you sand it, the smoother it's gonna get, the easier it is to lay it out.
You know, move your radius. You could potentially draft. You could just widen your radius, right? It's a small feature is what I'm talking about. It's 3 inches by 4 inches. It's a very small
like
feature.
This big.
Yeah.
I'm not worried about the fillets. I'm worried mostly about the planarity of that face. You see what I'm saying?
Planarity of that.
So these, like honestly, all this I could not care less about. What I do care about is just that these 2 points are planar to each other. And so, and if you sand this and this comes down to here and you widen the fillet, it'll make it kind of easier to lay out. You see what I'm saying?
You just not comfortable with it. It's a very small feature. I mean,
That is true. Would you recommend making it just bigger? But at that point, you know, for mounting system, we've had for the past 3 years, we've had issues mounting that front wing. A variety of reasons. What we did with the nose cone is because it's a nose cone. Last year, the biggest issues we had was we're trying to have a part that is water jet out bolt to hand drilled locations on the chassis. And let's say I have Stanton. Do you remember the wingspan of the front wing? 56? Yeah. Thank you. Let's say this is 56 inches, right? And you have 2 mounting points here. Any misalignment in these and a slight bit would now completely change that. And when you have heights here that you're trying to maintain, it becomes a huge issue. So we've always the front wing has always had issues with, you have like really large body that you want to be within a fairly tight dimension, yet at the same time the mounting point where it actually mounts to whatever you're locating it to are very poorly tolerated. You see what I'm saying? So like any little bit of misalignment in that is now going to make this whole 56-inch thing slightly to the left, and you're either scraping or you have just aerodynamically not performing like it should.
do you think you can maintain planarity on that thing?
I'm hoping so. We'll see.
I mean, I don't think you can.
I think it's going to be better than previous years, you know. I'm looking for better, not perfect.
Why not just make that a smooth face and then instead machine a plate that has that anglage one? That way you have a better control of your tolerance rather than hand sanding it.
A plate? So machine.
The spacers
So-
slanted like a wedge or something.
Yeah, so we did do spacers previously. What was that? Yeah, ship. So we did do spacers previously, and we have had a lot of issues with them. I don't know where you went. Yeah.
And issues.
Again, alignment issues. They weren't coming out where we wanted them to be. I don't want to spend much in every direction because they were 3D printed. Because we couldn't do them out of steel or out of aluminum, and we don't want to machine out an entire part for a spacer because it has to be fairly large. You know.
You're really that bad 3D printed?
Dude, you have no idea.
I work with 3D printers pretty much every day. I think I have a 3D printer.
So yeah, they were being that sense.
I mean, you can do pretty good with 3D printers. 3D printers are pretty good nowadays, and I think you could probably do pretty good with a plate like that. Like you have to bring down your resolution down to like 0.05 or something like that. But I think you could do. I'm just saying this is going to be a pain in the ass to get right.
I was thinking back on Mikey's pockets for the chassis, the bottom two. We spoke with him about it, and he said like he didn't have too many issues with that. Remember the suspension ports that were inboard?
Yep.
That's why they had the bottom two halves to come out. He's like, this is fairly larger than that with less of an elevation change. And on
So
top,
you said this was larger than that, or?
so this is larger in this direction, I believe, and it has less of an elevation change. Whereas his are sucked in quite deep. You know what I mean? So let me.
These are also
Yes, so they're in, right?
Not bosses.
Yes. So therefore, on sanding, you will have the same issues because you're digging into it and you're reducing clearing, right?
Potentially.
But yeah, so he didn't have issues, and I was like,
So
look at this.
Mikey's though was a little bit unpreventable, right? Because his suspension point was inboard where he wanted his chassis to be.
Yeah.
So he had to do that.
Yeah, let me get the line. So yeah, he did have to do that, but for me it was cost benefit analysis. I'd much rather have a chassis that's flat where it's supposed to be and have like the benefit of that, and from what I've seen from his side, the risk wasn't too high.
What's the plan if you can't get it flat?
Can't get it flat?
If the sanding makes
Well,
it.
it's more so for the hard point than anything. It's not necessarily like, if it comes out misaligned a little bit, then you just open up the hole a little bit on the wing. But having a hard point there, something that's not like a spacer inside of a carbon part, is gonna be very nice. But you don't want at the same time the hard point to be, what is it, like 5 or 6 degrees off to which the chassis, this surface itself is. I can't remember what the number was, but yeah. So yeah, we're gonna keep going. I'd love to talk to you after about that, just because for the sake of not keeping everyone else here for too long. So yeah. This is still mine. And then we have the what's it called? The access panel. So the width of it was constrained by the two chamfers. The height of it was based off of the previous width getting in front. So you know the old bulkhead size? That width was able to fit the largest components. So therefore we made that the height here. So if I have, let's say, a brake assembly, whereas before I could just put it in like this, I would come from the top and then rotate it and set it down. We're still gonna have the same access on the front. This is more so just ease of life, have more access. And it reduces some weight. It's also all flat, so you cut it out. That's gonna be in the mold. It's gonna have that surface. And then you can just put a flat panel, 2 clouds of carbon, cam locks, and bolt it down. Yeah.
You're gonna do that feature in the tool?
Yeah.
Why not just cut it?
I was thinking about it. I'm still half and half on it. But for me, the tool, just a nicer finish on the edges. I can't imagine doing stuff or anything because it's on the top. It's just kind of doing it like this, you know?
So what kind of feature are you doing that to make that?
Same as you would do over here. The tool is going to have the actual foam tool is going to have a divot coming from the top. So when you lay it for the infusion, you're just going to have the tool, but the male tool is going to be just lips like this and put your core up against it, just like any other hole, like a bulkhead. And you can see a bit better here how there's like these little transitions to keep this face and that face perpendicular, and this one and that one, and then just that's it.
Alright, so one of the things in the past that we've had problems with is the steering wheel itself. When you go to turn it and everything, it runs into your legs, and it's really uncomfortable for drivers all in all. I know 2017 and 2018 had this problem, or if it's not, it's 2016, 2017. So one of the things this year that we really were kind of key on is making sure that we have enough space for that, and that's what brings the steering wheel up, along with keeping that the top of the chassis there, and making sure everything's comfortable for the driver and all of that. Along with that, the firewall, the angle is going to stay at 50 degrees. This is for driver comfort and also for the powertrain packaging in the background. So for example, for the fuel tank, battery mount, any of the things that data acquisition wants to put back there. That will provide them enough space so that we're able to house everything that we need to, and then the angle itself will be nice for the driver, as we have tested with the ergonomic jig. And so, in regards to torsional stiffness, one of the things that I did discover was torsional stiffness is about the entire car in itself, as we had mentioned earlier. You have to do some sort of test in the entire thing to be able to properly measure, okay, what is the torsional stiffness for this car. One of the ways that we can kind of help it is by manipulating the front bulkhead area. The way we do that is playing with the front bulkhead geometry to make sure that we can maximize that polar moment of inertia. By maximizing that polar moment of inertia at the front bulkhead geometry, you can tell this is technically the smallest portion of the car. It then feeds back, becoming bigger and bigger. And from that, the polar moment of inertia gets bigger and bigger in itself. When dealing with torsional rigidity, this is the one aspect of it that you can kind of manipulate and measure, because the other aspects are your torque, your angle, and your material properties. And for the entire car, we don't really have that. And doing a torsional test on just the driver cell itself wouldn't be much good use, as it being bolted to everything else in the car. So maximizing the front bulkhead polar moment of inertia was something that was a priority, and from that, we are looking at having a greater torsional stiffness for the rest of the car.
Did you say testing the driver cell itself is not a good test?
Yes.
I disagree. If you could do a finite element model of the driver cell and then a torsion test of just the driver cell and validate that model to like help a percentage, I think that's what it is.
How would that work into, because that's just the driver cell, one of the things that, yeah, how would that work in the full vehicle?
You can validate a model, then your finite element analysis has work to it, right? Judges are going to see your finite element models, and they're obviously going to think, you guys know that you experience it, and you get away finite element model, right? But they're judges, they're just going to see that, right? So if you can say, hey, I validated my model, then all of a sudden your finite element model is worth, right? And then you can go on to making a full car model like I tried to do. And once you have one model validated, it's much easier to use that as actual design analysis.
But with like a chassis model, is there like a lot of differences during just like the part, the composite part, the entire side of the car essentially? You see what I'm saying? That's a little odd.
Maybe.
So if you're doing a model of just the car, or of just the driver cell, and you're able to validate that within, let's say, like 10%. If you're doing the entire car, there's so many differences in the way in which you have to model it, that you could say at this point, like, okay, you're not comparing apples to apples. So if you say like one FEM model works, great, but if you have this other one that's very different from the first, can you say that, oh, well, this one works, or this one will? You know?
Yeah, you can.
I think so. You think they're similar enough that?
Like, model correlation is everything in my work, at least. So, like, if you can correlate one model, and like, the driver cell is the difficult part, right? I don't know if Luis is here. Hey. The steel tube roof frame that you've been asking me about, it's just a beam element model. Beam element models are like very reliable, they're very easy to make, right? The driver cell is a composite honeycomb, which is very difficult. There's a lot of moving parts there, right? So like going from a driver cell to a driver cell on a steel frame, like judges will believe a beam element model before they believe
So
your
you're saying like the beam is good. So the beam is very easy to assume that it's true, and if you can assume the carbon's true, then you put them together.
You have a lot of validity.
Yeah.
Validity that way, yes. Yeah. I wouldn't say there is not any worth to it. There is some. I would see some worth to it. Yeah, I think it, but just my 2 cents.
All right, and another portion of this is comparing the driver cell from last year to this year. One of the things was last year's driver cell was made for manufacturing. It was made so it was very squared, so it was easy to lay up, easy to put the core into, and easy to manufacture basically. But however, it was very big, boxy, and therefore resulted in heavier chassis and everything. So one of the things that I would want to do this year is I'm trying to reduce a lot of weight off it and seeing how that goes. Starting with that, you go and look at the surface area and everything. One of the things is this is a 5.7 meters squared for the driver cell, and for the new one, it's 5.44 meters squared. Doesn't seem like a big difference, but it actually is. One of the things with it being, it's the chamfers that we have included for visibility and everything help play a big portion into that, and along with the access panel for removal. That all helps play into helping the driver cell geometry itself become lighter and being able to produce lighter driver cells in the future.
Did you get your surface area calculations from the model on the left?
Yes.
That's the wrong one. That one has a smaller front bulkhead than the actual one.
Oh, you're saying the flange?
No, yeah, the front
The,
bulkhead.
yeah, flange.
That one is much smaller than the one that's actually on there. I noticed your guys' front bulkhead though is still big. Why is that?
The reason that it's still big is because we're keeping the same location, so that bottom half
That's
is.
gonna change. But the
Yeah.
flange itself, which will
What
hold.
picks up on the front bulkhead?
So if I change this, it's loft, there go all these 3 points.
Yeah.
So we weren't going to come in like that, see what I'm saying? This action is one loft.
I'm talking about the inside cut. Why is the
So
inside
this
cut so
inside
small?
cut, okay, I was going to do that one next. So the inside cut, the reason that we made that small is these bolt holes, right? We're gonna bond the bolts in on the inside. And so the issue with last year, the year before that, do you remember bonding those things in? One of the large issues was because, I'm gonna get that marker again. Sorry, you hear that? If you're coming in on the inside, there's gonna be a fillet there, this always happens. The farther you get from this, the more planar you get. We always have had issues coming here and bonding the bolt to a fillet. By keeping it to the same amount, I move this bolt hole over, bolted it over here, and now it's flat, instead of bolting.
Do you know why the front bulkhead is so big on Sam's chassis?
No, honestly. The one thing I do know is, I believe it was made for the structural nose cone. I believe that'd be one thing.
No. So the one on the left was the original model that we did. We actually started a tool for that front bulkhead as well, but we failed that tool twice, by the way, so don't ever try to do that. But we had an oh shit moment because we got our SCS back on that and we weren't passing our front bulkhead fasteners. So it got so big because this was in this was like March, April, I want to say. So we were getting down the line and we were like, okay, how do we fix this, right? And so the front bulkhead got so big because we had to have so much area for those. So much. I think I can't remember how SCS is dictated, but I want to say it's dictated by the distance from the edge.
Yeah.
For those. So that has a huge distance to the edge because we said, fuck, we're not passing, we need to pass like right now. So we made something that was fat, and that was to make the current laminate properties work, right, in the current market.
Yeah.
So when we got, the first thing the judge that we saw was, why did you make your front bulkhead that huge to make it smaller? So, so for one, it's heavier that way, right? For two, you have a smaller access panel, right? And I know poor Eric was in Michigan, or did you go to Michigan? You went to Michigan, didn't you? Someone was in Michigan with us, and they were working on the brake tunnel assembly, and they were just having the worst time because of the god awful small port. And I know you're adding a top one, but you will still want to go through the front one as well. Just as a
No,
side
that's what I didn't close it. Yeah, that's what I was very conscious of.
So I think what you're saying right here is not necessarily the best answer, that you were driving the front bulkhead bigger for these fastener clearances. I think you can come up with a better answer for that.
Okay, that's good.
But overall, this is the weight reduction from geometrically from last year's chassis to this year's. What I did was I took last year's laminate schedule and based it off of that coming out of the tool. Came out to around 55 pounds, and then applying that same laminate schedule in the same places to the new geometry. It came out to around 41.5 pounds.
What was the actual weight of last year's driver cell?
The actual weight of last year's driver cell was 62 pounds.
Where'd that weight come from?
That weight came from after post-ops and everything, weighing on scale. Coming from there.
I mean, there's a difference between what you're calculating here and what the actual weight was.
Yes, the one thing I focused on here was because I had the data for what's it called? Because I had the data for the plies that we actually had and the panels and everything, I wanted to use that data itself to actually be able to do a comparison because having those panels and everything, those are actual real numbers and things you can kind of scale everything off of, where you can't exactly throw in the amount of hard points, the different types of reinforcement plies, laminates, front roll movement, all that, force plies. So there's too many different variables going in there, which would cause some sort of faulty data with that.
For this weight model, we have a discrepancy there, right? This last one was heavy in theory. For the final weight, we did add that into the weight because we're assuming, we can't assume that that's not gonna happen this year. You know, let's say we say theoretically that you'll get 41. What happens when it comes to all those things that we don't have complete insight into? How much weight are you adding in course price? How much weight are you in course supplies? All that kind of stuff. So this weight that we end up using for Eric's stuff is actually weight range. Is
one thing, just to make sure that you guys understand what this isn't a actual, like, how do I put this? It's not representative of what it would be with the actual implied social and everything. What I'm showing here is the difference in the weight of geometry. That's what I'm showing.
So this is like pure, this is
pure surface area weight regarding that.
I understand that, yeah. So okay, so last year's chassis was 60 some pounds, you said, right?
Yes.
And your weight model here is saying it's 54.5 pounds or something like that, right? So what does your number mean then? You're saying it's not an accurate representation, right?
Mm-hmm.
Why are you using it then?
This isn't what we're using. This is literally just to look at, this is one slide of more coming up. This is solely looking at what is basically the percentage reduction in the surface area being weighted properly. What type of surface area is that? Because if we did it purely just, okay, you move 50% of your surface area, well, what if you're moving it all off on your main bulkhead support versus your side impact versus your, you know? So this is more so a way of dividing the surface area and categorizing which surface area does matter and doing that based off of rough numbers, essentially.
I mean, I think you do that with percentages too. You're putting rough numbers here, so I'm thinking this is what's going to be the actual thing.
No, this is not. This is not. These are like instead of percentages.
Yeah, we have design, solution, weight, and then you have weights. So this makes me think that this is your solution, right? You see where I'm getting at, right?
Yes.
Yes.
Okay.
One thing I will say is with this, I understand there's some sort of discrepancy in the sense of like, okay, there's some variables moving around here. From that, basically, it's more so just a representation of the surface area. That's really what the whole point of this was. There's again, this is just going back to what was said earlier. This is just geometric weight with the actual apply schedule that we have developed and everything. There will be a new weight, and that's the more target weight that we were kind of getting at.
Which is why you also see we use tiny last year's surface or apply schedules, because we're not trying to give an estimate of what this car will be, but more so compare apples to apples.
Yes.
Okay, that makes more sense now. Okay. One last question. I know you've been texting this a little bit back and forth. Did you use the inside or the outside sources?
Outside.
And is this going to give you a conservative or an aggressive answer?
This would give me probably it's probably a little bit more. I wouldn't I'm not sure, to be honest with you.
Okay.
Real quick, I think most of the problem here is just with the presentation of this slide specifically. But one small problem that I have, you probably don't need that many significant digits. Also, you could probably just have, one column geometric weight of the driver's cell and then FBH, whatever. Next column be, this is last year's, and then just pounds with like maybe less significant digits. Another cell, instead of a whole different table, maybe just one more cell or one more row or column. Sorry, one more column for the next year's one that you're doing right now.
We're saying like merge
And
this.
Yeah. And then one more column for percentages. Just divide one by the other, using cell, drag it down. And then present less of the weight and more of the percentage.
That's a good idea. I like that. For system integration and everything, two basic routes we'll be going are just regular bolts for things like suspension, certain powertrain components, and aero, standard number 1032 going through that, and then certain things for epoxy for stuff like the fuel tank, battery mount, vacuum bolts and things like that, going through like that. And then this is kind of the manufacturing plan of everything. Some of the foam blocks, send foam blocks out to be machined, receive them back for layup. And then one of the things that we're looking into this year, instead of doing infusion, is something of a pre-preg layup. Going into that, I'll touch a little bit more of that in the next slide. From that, pre-preg layup, and then we'll have the tools for that. I'll go to the next one. So with the pre-preg layup involved in everything, before I get to that, for the foam blocks, one of the things that was suggested to me by, I did talk to Mikey a lot about this, trying to actually get a nice plan structure for manufacturing. One of the things being, when starting for the foam blocks, basically vacuum bag them so that it's a nice seal and it bonds together properly, so that when it's sent out the machine, there's no sort of like obscurities in the actual foams itself. It's a nice smooth part. From there, getting foams back and after prepping and sanding, there's been a lot of we've been bouncing back and forth wet layup, infusion, and pre-preg layup itself. Infusion, we've had a lot of problems. It's a problem, yeah, basically every year, whether it be a tool not coming out right, or whether it be dry spots or something's wrong with bagging. So we're kind of going back and forth with that between wet layup and infusion. And noticing that 2015 tool where pre-preg, talking to Mikey about it, one of the things that we can do is after we get the foam blocks itself, put down a gel coat, which is sold by PTM and W. And with that gel coat, what you have to do is you take your first ply carbon, lay it down on the gel coat, basically let it so that it bonds to it and everything properly. And then once that's all nice and set after some cure, you are then able to lay up on it like a regular layup. You then can throw it in the oven and let it cure. And once it's all said and done, you have it out. And that first layer is basically your tool. That first layer is that most important layer, as that's basically how it would be. That was what the surface finish would be on and everything. But this here in itself is to me, a much safer and cleaner route going rather than an infusion, because there's a lot less variables involved. The infusion is already embedded into the pre-preg, in which you can stack the layers on top of each other and then cure all together like that. And from that, basically, it's easier to control. Okay, look, this is where we carbon. It's not like, okay, we're missing resin in this one place and therefore results in a dry spot. This is a more accurate and easier way to get the tools set out.
Are you going into more detail on this later, or is this?
This is it. This is a very more so rough idea. This will be more developed within the next month or so. This is what I have on this now. I do not have like the type of gel coat that I use. I don't have. We do have a lot of pre-preg, I will say. We got a lot of it from Boeing this year, but we got a big donation from that, so we have more than enough to handle all of that. I am in contact with Scott, and him and I talked a little bit about this, and I'm going to be giving him some more calls throughout the next couple months to make sure, okay, this is the proper things that we need for it. And yeah, in regards to the foam blocks, what is it? We have still yet to send it out for machining. However, within this next week, we plan on sending it out. And with that being said, what happened there basically was our sponsor for the foam blocks fell through. We have still yet to hear back from them. They still yet to send us the proper amount of foam for everything. And yeah, so next week, going in, we can get some foam from John's shop and then put it all together and then get it sent out to our manufacturer.
I don't want to take too much time talking about this. We can come back later. All right. Who's machining your phone? Just yours.
Chad.
Nice. Put a tolerance of quarter inch on it.
Okay, so since you are running with a carbon chassis. We will have to fill out SES again this year. So SES, as you guys know, we have to provide driver safety, and we have to prove that our carbon fiber chassis is safe, adequate enough in comparison to the steel tube chassis. With that, some of the areas that we take a look at, we take a look at the side impact, the front bulkhead support, and the front bulkhead itself. Some other tests we do, apart from the shear test and the 3-point bend, we do a lap train test and an anti-submarine belt. As Nick said, we also have the impact engineer attached to SES this year. But as far as the goal this year, 2020, the goal is basically to reduce 10 pounds off the chassis. With that, this is kind of my design solution that I broke down. So I went from the data sheets, eventually moved on to the classical lamination theory of composites, and then I basically reverse engineered the SES equations that are posted in the actual spreadsheet. Right. So the material that I'm actually that I chose was just a plain weave. It was the Cycom T300. So it was actually the weakest strength, but it has the highest strength to weight ratio compared to all the carbon that we have in our whole library. With that, all the resins were different, so I had to choose this one because we've run with it a couple times. So mixing resins was something I didn't want to explore too much into. Apart from that, the data sheet was complete, therefore most of the predictions would have been accurate. As far as what else, it's a plane weave, so the quasi-isentropic condition can be met easier. And that's just that, but we have 3 wells. So quantity is something we definitely have a lot of. Apart from that, with our core, we're sticking to 1-inch aluminum core and then 3/4-inch Lennox honeycomb. So yeah, as far as how I'm designing the laminates, I'm basically basing it off the stiffness matrix that's presented by the composite theory. So basically, I make them symmetrical. If I make them symmetrical, your D matrix goes 0. From there, a lot of the calculations actually get a lot easier in terms of calculating stiffnesses and moduli. So apart from that, the actual core changes the inertia. So in the end, it's really just about how thick you want your plies, how thick you want your core, and all that really induces change in your laminates. So if you take a look here, on the left, you see that it's unsymmetrical. So that creates a lot of calculations. And as opposed to the right, where you have something that's symmetrical, a laminate being symmetrical over its axis, and so you'll have something a lot more basic to calculate and something that produces a lot better modulus. So we continue. Kind of my process with it was I did test something just randomly, and this one did pass kind of the most difficult SES requirement, which was the vertical side impact. So this was an 8 harness. It wasn't necessarily the T300 that I'm rolling with. But from this 8 harness, I basically get all the parameters that I want and reverse engineer my laminates to kind of reach the same properties as this one. So for example, I'll have the best tested panel. I will tune the stiffness. And from that, with the carbon properties, I will basically tune the modulus and inertia. So that's for a 3-point bend. And in the case of shearing, I basically try to find the minimum amount of plies for the shearing requirement with SES. Okay. So the first laminate I made was the main laminate and the rear. So in this year, I decided to combine the rear and the main laminate in the case of weight reduction. So it's basically a 3-core 3. The real requirement is for it to reach 4,000 units of shear. In the first peak, it doesn't quite reach it, but around the second peak, it does quite reach it. I did predict that you needed about 4 plies for this. The reason why I wanted to shrink it down is because I knew that around the second peak, there's always a higher peak in shear. Hence, I decided to lean it out. But as far as that, the best predicted laminate from the 8 harness was around 4.02 for synthesis. I predicted 1.22, and the actual stiffness was 1.10. So it's under, so it's undertuned to what I needed it. That's because the actual value I needed for the vertical side impact is not the same as the actual main laminate. But from there, SES did kind of shoot out all these numbers that I, yeah.
2 questions for you there. So
Yeah, go ahead.
main laminate, so this is your front bulkhead support?
Yeah, front bulkhead support and the rear.
Okay, and then your rating DDI, is that what you figured out in feedback?
No, I actually predicted this,
Or handhelds?
handcuffs, yeah.
And then that's your actual?
Yeah.
Yeah, good job.
Thank you. Yeah, so basically this is the main laminate and for this part of the chassis. So if we move on. Horizontal side impact was a little bit different because it's not quite like the vertical side impact that you need an energy requirement. It's more or less a shear requirement. So again, I calculated the minimum amount of shears, and I made sure to tune up the stiffness or the EI. So I increased the moment of inertia, and I try to increase the modulus as much as possible. So as you can see from the 3-point bend, it shoots straight up, and the actual shearing as well, it shoots up a lot higher. So from there, these numbers basically dictate that the laminate does pass the requirements for the horizontal side effect.
Or what did you predict for your shear? Or did you do any calculations for shear?
So as far as, like I said, the way I predict things are more or less the bare minimum I need, like the bare minimum thickness I need per skin. So that's basically what I found. I found that 6 plies was the bare minimum for the vertical side impact, because the vertical side impact and the horizontal, they share the shear. Yeah.
So why was your shear higher than what you predicted? Just, what do you think?
It could be maybe because the property, so I am working with basically carbon that is expired. Perhaps when we process this laminate, we did a better job as opposed to other times, because usually you do get dry spots and that does harm the actual performance. Okay, so as far as the vertical side impact, I try to tune it as close as possible to that 8 harness I got the first try. So I got it as close as possible to the predicted and the best laminate, which was pretty decently close. But from that, I also calculated the minimum amount of plies, which was 6. So this was 8 for 8. I buffed it up so I can basically put the energy requirement here. So from the energy requirement, it actually passed 179. The requirement is 166. So we're good in the vertical side impact.
What was your failure mode on that then? For 3-point bend?
The failure one?
Yeah, what was the failure mode?
Shear in the core. Yep. Alright, so from that, SES, actually all the composite stuff is complete. It's passing so far, so that's good news for us, especially since SES has been moved up for us this year, so that's good. In the case that we do get an upset with SES, we do have some 8 harness panels that pass most of the requirements, for example, the vertical side impact, horizontal, and the front bulkhead support. So we do have laminates that could be substituted in the case that we do have an upset with SES. So as far as what's next, we do have to import the steel tube information, and after that we will do the impact engineering. So from that, I decided to implement the new laminates into the new chassis design, and with that we found that the theoretical tub will be around 27 pounds. In comparison to 2019's chassis, that's about a 27-pound difference, just because of laminates. Okay, so as far as the manufacturing plan, I have to finish SES, of course, and I have to start preparing these laminates for the actual mold, and I have to help lay up the mold because that's something new. As far as how the chassis will be made, we're going to do a skin run, core run, and then from there we will have a chassis ready. So something we've been noticing, at least with this time around with our laminates, is we do have a lot of dry spots. It's unfortunate, and then for a while we were getting a lot of delaminations, as you can see there in the middle. And then some risk we always see is because of the core splicing, so that does add a lot of weight in terms of manufacturing, so that does harm our theoretical weight.
Why do you think you're getting dry spots?
Dry spots were mainly coming from our film release. We weren't taping it down properly, and not just that, we weren't holding pressure as much as we wanted.
How much pressure were you holding?
Let's say 25, 24, maybe 25, yeah.
Thanks. We usually try to shoot for like at least 20, at least, even though that'd be kind of a sketchy.
It doesn't hold very well sometimes, but
why not?
Usually the bag pops. Usually our chromate doesn't stick well. Usually there are our ports are not as functional. So in the beginning of the semester we were mixing resins, and the ports got chugged with resin. So we're having some
issues there. Chugged with resin.
So yeah, they're like, yeah, they basically can't suck up a lot of air, but do what we got.
will say, we will be getting new Fords. We do have a new shipment of coming in, and new bagging material from AirTech for all of the manufacturing of the driver side.
So what resin system is this T300?
It's T300 970.
Is this the stuff you got from Boeing?
Yes,
So that's an autoclave only resin, right?
that is an autoclave.
And you're running it in a vacuum bag only.
Yes, that's correct.
Do you have any concerns with that?
Yeah, a lot of the properties aren't as intended, especially for the moduluses in both directions. They're not as high as I expected. So with the calculations I'm doing, I am incorporating a correction factor based off the the percentage of property lost because of, it's expired. There are some wrinkles on the actual carbon, so it's not performing as well as we intended or it's posted by data sheets.
What's your approximate strength on them?
So
Ish ballpark, yeah.
So it depends. So usually when we mix resins, I do see like a 40% drop, but when it's T200 alone, it's only like a 20% drop. So yeah, a lot of different things vary. With the 8 harness, I did see like a 40% drop because we were mixing two resins, and then at one point we were mixing 3 resins, which was crazy. Yeah.
Cool, good stuff.
Okay, so as far as what's next, some risks, of course, are delamination, dry spots, and then waking. So with that, we're gonna make sure that we debug the first ply. I was here last year for the actual layup of the chassis, and that was something that was not properly done. So we gotta make sure to debug that first ply. Apart from that, we gotta make sure the bag is well and safe, no leakages, no pops. Not just that, we'll be implementing the 5-minute leak test like always. As far as dry spots, we will make sure to flash tape everything down to have a very tight pressure around the film adhesive, film release and the fill ply. You gotta obviously make sure for bridging. And then as far as waking, we're gonna take special attention into the actual geometry. So when it comes to the actual chassis, we will have templates ready from the core to make sure that core splicing is kind of reduced.
So you're telling me you're gonna reduce core splicing?
Well,
Nick is telling me he's gonna be core splicing the shit out of that.
So one thing with the core splice is last year we used, it was like a liquidy stuff,
Yeah, the injector stuff.
not fun. We got
sheets from Boeing. We got 2 pallets of the sheets. So one of the things we're going to be able to do now is accurately measure out how much core splice we need around there, and accurately cut out in the core what it is that we need for it, and be able to put it in. So by that alone, Nick's ridiculous thing with the core splice and everything is acceptable compared to not only last year, but from the method we are going to be using going forward.
we have a lot more control with it.
Yeah.
You guys are saying different things.
So the reduction in core splice, we think overall we will have a reduction in core splice.
Yes.
Not because we're using it in less areas, but because we're using less of it in one area.
Okay, so still to lean. So as we all kind of know, the rear frame is supposed to house 5G components, and it also serves as a mounting surface for suspension components and aero components. And this rear frame is designed for factor safety 1.5. The goals for this year's rear frame was to reduce weight or maintain it at 25 pounds or less. This was not accomplished, unfortunately, because the rules changed. Now they require thicker tubes, therefore our weight went up by a little bit. So right now, as of right now, Software says 27.49 pounds. And so another goal for this year is to keep the intake with an envelope, and also to ensure rear control forces are directed to the nodes. So parameters, as you can see, and as you can sort of remember, the rear frame hasn't changed much, and that's because mostly suspension nodes or pickup points are not changing at all this year, and so all of these nodes are set. So I cannot move any of those, and if I want to add or space them out in any way, I'm gonna change that geometry. So therefore, I'm very constrained. And so, I want to maintain the minimum wall thicknesses as stated by the rules, and also So the performance criteria for the rear frame is that the elements are loaded in only tension and compression because they are connected to one another. And the major loads are by only elements. So design solutions, can you go to the next slide, please? Thank you. So this is last year's problem. As you can see, the force over there is acting on the tab by itself, and therefore the tab is at risk of failing. So therefore, I lowered that mounting point, and now the force should be acting at that node directly to it, and so the force should be distributed through the tab and the node, and not just the tab. Another solution is that we want to keep the intake with an envelope, and this is to pass tech inspection. So here's the line that's going to be drawn from the top of the main hoop to the tension to the tires. And so last year, as some of you guys may know, they had to switch or swap intakes in order to pass this test. And so we want to avoid that. Therefore, I increased the main hoop height by 1 inch. And another problem was that the bearing block mount on the engine, the bolt was yielding, and therefore Mitch redesigned the whole bearing block, and now it's going to be mounted on this member here, so it's over there. And I have, sorry?
The bolts were yielding?
The bolt was yielding, that was holding the bearing mount. But that was only, it was only supported by the engine and not the rear frame itself. So Mitch redesigned the bearing block, and now it's going to be attached here. For system integration, the chassis will be, the rear frame will be attached to the chassis by tabs, welded tabs. And these are going to be bolted down with 5/16 bolts. And the engine will be, the engine mounts will stay the same as last year. And they will be machined and welded onto the rear frame.
Are those what materials?
Sorry. So the engine mounts are steel. Probably like 4130, same as the steel tubing material.
Is there an FAA on that in the rear subframe?
No, not yet. We're still in the process of that. I tried running FEA on VMAP, but it didn't work well with the geometry, so I'm still working on that.
So you said that the two pieces went out due to what changes with this, like what tube size are you guys using then?
And well, so the rules state that okay, so certain parts of the rear frame need to be a certain thickness, and so for the majority, it's the ones that we mostly care about is the main hoop braces, and the main hoop supports, and so the main hoop supports went from like 47 thou to no, I'm sorry, 47 thou to 49 thou. So, and also for non-structural tubes, it changed from 35 thou to 47 thou. So it went up by quite a bit. And so the manufacturing plan is to have the tubes laser notched, and they will be laser notched by CDR manufacturing. And the rear frame will be welded, and I'm going to be welding the rear frame. And the jig will be made out of steel sheets. It will be water jetted and welded as well. And I'm going to be using some clamps, some magnets, bolts to hold down the jig table, and some sensors. Yeah, I'm going to show you right now. And so, what else? So some critical parts for the rear frame is that if the jig is not properly aligned, the rear frame is not going to be properly aligned. It's going to take a while to get the tubes aligned correctly. So, go to the next one. So here's my,
Sorry,
yeah.
What filler rod are you using?
Sorry?
What filler rod are you using when you're welding?
It's I don't know at the top of my head. I think it's like 332 filler rod copper.
We use it's SD80, 80 SD2. So you guys usually have 75, not 70, but 80 has a higher tensile strength. That way you don't need to
Yeah, we're not gonna control the tubes at all. And so this is the jig. This is still a work in progress, but the way that I thought about this is that last year I think they overlooked the steps of actually welding the chassis or how they were gonna go about it. And so there was a lot of misalignment issues. The water jetted jig was not aligned because they welded it at the wrong spots. So therefore, like if you weld so this is so, okay. So this is kind of like what the jig looked like. So they welded these parts right here into the plate. And so therefore this one, like it would and they also welded here. So the jig would actually like tilt a little bit. And now the tubes are misaligned.
So how are you
And
gonna fix
so,
that?
sorry?
How are you gonna fix that?
The way I'm gonna fix that is I'm actually making these wider, and I'm actually welding in the middle of that, so it doesn't like it doesn't move side to side. It's only gonna be at the middle.
How are you gonna hold it in place?
Sorry,
How are you gonna hold it in place? While you
magnets.
weld it?
The
So
jig.
you're gonna have some issues. It's gonna move around no matter what.
Yeah, it's gonna move around, but I'm gonna try to keep it in place with magnets.
Isn't that how they were doing it last week too?
I'm not sure how they welded it, but all I know is that they moved, and you can see it like from the walls.
You need to add another support there. Right, it looks like we have 90-degree angles there, but as soon as you add that weld there, it's gonna warp, it's gonna pull.
Yeah.
You're not gonna have it. So, yes, that was the first time we did it, and I think that was the best time that we had. That was the best jig we probably had. Those supports with notches prevented your cast from actually moving after. So yeah, you'll still use the magnets, but even just magnets by themselves, like the setting, it's still going to move.
Add extra Okay. Yeah. Well, this is a jig still in process, so if you guys have any more ideas, I'm very open to them.
Yeah.
Yeah. And so basically, here's the process. It's gonna be welded like from the ground up. And if you go to the next one, here's the rest of the tubing. And so these are actually tubes, and within the tubes there's gonna be sort of like a sleeve. And this sleeve is there's gonna be a set screw in which I'm gonna adjust heights. So therefore they can be utilized for several parts of the rear frame. And so this C-clamp right here is going to be tag welded into another sleeve, which is also going to be attached to the tube. So it looks kind of sort of like a T into the tube, and then you have this other tube connected to that, and then in that tube there's going to be a sleeve, which is going to be set with a set screw, and that one can actually rotate, so we can get those angles of those angle frame members. And so the manufacturing plan is to have the jig water jetted, and I'm gonna weld the jig. As I'm doing that, the tubes are gonna be sent out to get notched, and the main hoop is gonna be sent out to get bent. And then I'm also gonna be machining the engine mounts, and then when those two are done, I'm gonna be welding the rear frame, and then lastly weld the engine mounts and weld the tabs that go into the frame, and therefore we're gonna have the frame completed.
Who's bending your main hoop?
CDR manufacturing. And so some of the risks here, as we have mentioned before, misalignment due to welding. So for that, I'm going to be using magnetic levels to make sure everything's aligned. Angle measuring tools to get more accurate angles, and then obviously get the jig aligned before the tubes are welded. I'm sorry. And I'm also accounting for any misalignments due to notching, because notching is it's not tailored to a certain tube, and it's also like it looks kind of different from the model trims to the actual notching. So therefore I'm accounting for that. And then if just in case an engine mount fails, If it's one, it's just we're gonna notice that right away, and then we could get that fixed. I could have extra engine mounts to replace the damaged ones, and then where's my brochures? Oh yeah. So if just in case another from the driver cell and the rear frame bolts shear, we're gonna have extra to replace it. But we do have 3 tabs connecting the driver cell to the rear frame, so I don't think we should experience any call from those. Yes.
Did you already get a quote from CRD?
No, we haven't. Yeah.
For pending, they charge a lot more than this launch.
I think they said like $2 grand or 1.8 grand for bending and launching.
Yeah.
It was pretty cheap. So that's something we can also do.
Just out of curiosity, where are your engine bolts at? Is it steel?
It's steel rod material. So it's basically bored out when machined.
Why do you use titanium?
It's expensive.
I gave you guys a whole rod.
I don't think anyone.
Yeah.
Yeah.
Can you take it?
I have his rod. Yeah. I have his rod. Yeah.
Now we'll be moving on with so right now, if you want, we can have like a food break. Or do you want to keep going?
I mean, we're
We're actually on schedule right now, so we did schedule a 30-minute food break. So if you guys want to talk to us or socialize, that is in the schedule right now. So yeah, let's take a food break. Yeah.
I just want to start off. I made a little typo with those torques should be the same. That one it should be 48.5 minutes. So for my problem definition, I want to, like Erwin was saying earlier, I want to increase the final drive ratio to operate at a higher RPM range of about 8100 to eliminate the need for first gear, and I'll get more into that in the next slides. And more on the structural side, just designing the system to withstand the 48.58 foot-pounds of torque at the crankshaft. And as for my constraints, packaging was a big constraint for me because if I'm trying to increase the final drive ratio, that'll be done by either decreasing the drive sprocket or increasing the driven sprocket. And so since I'm working in that little volume in the subframe, I'm really constrained on sizing. And the requirement is just making sure that all my components don't yield under that torque. Just going into my parameters, I'll be changing the final drive ratio, bearing block mount location and geometry, and then the tensioning method. And then all this will affect the operating RPMs, the load distribution between the different mounts, and the tensioning efficiency. And so what Adrian was getting in before last year, not only the bolt yielded, but the mount on the engine yielded too. And I believe this is because it was in single shear. The bottom mount's sandwiched in between the chassis and the engine, so it's in double, but the one they were using last year, it was in single, so it was putting a huge moment on that bolt and the mount. So going into my design solution for eliminating first gear, Erwin was kind of saying how we can only upshift or downshift by 1 gear at a time because we have a sequential gearbox. And we were running into an issue where when we were downshifting from second to first, we get stuck in neutral. So just to mitigate this, we want to increase our final drive ratio to operate at higher RPMs. And going through my design process with this, as you can see here, I was just kind of working this little triangle and putting different size sprockets in there. But one other constraint that I have is that the driven sprocket has to have a 120 degree of chain wrap just to make sure there's no power loss or slippage. And this is a function of the center distance between the two sprockets. So as I increase the sprocket size, the center distance will have to also increase just to maintain that 120 degree wrap. And after I got my link length, I calculated the wear on it, and there'd be a 0.3 linear tension distance. And so that's that construction circle, just showing that everything will be constrained in it won't hit the member of the chassis when it's tension.
Question. Will this first gear make a big difference in acceleration?
I'm sorry?
Does first gear make a big difference in acceleration, like in actual?
The timing?
Yeah.
I wasn't really looking at the launching purposes. It was more for like endurance.
Okay, yeah, I agree that you won't really need first gear for endurance.
Mhm.
It's not really going slow enough to actually use first gear,
Mhm.
maybe in some spots, but to get out of it in the second gear. But I think first gear would be beneficial for acceleration.
Our fastest time for the second year. So, yeah.
Yeah, like I mean, but even for acceleration.
They sell that's actual that launching second faster than first. For our for 19 cars.
It isn't actually beneficial for acceleration.
What's your guys' vehicle speed and idle in your second gear, your new first gear setup? Like how slow can you drive before you stall the motor?
Like the idle?
He's asking at 3,000 RPM in the second year.
I don't have that off the.
That's good.
Yeah, I ran a script with just all the different final drive ratios from, I believe, 18 to now, and it was just comparing how the speeds are decreasing as we're increasing our final drive.
You'll want to make sure you don't have too high of a vehicle speed at 3,000 RPM. At a certain point, you're going to have to start slipping the clutch just to try to get out of corners, and somebody might have messed up a little bit or overcooked or something like that. So being able to drive out of a slow corner easily is something that really helps your guys' actual lap times at comp.
So we've taken that into account with our autocross side of the parking lot second year idling around. Just idling around slower than what we expect to be the slowest time at any autocross or endurance event. So like our slowest time, our lowest RPM is 4,000 second year only. With a very tight autocross course. So we're not even hitting the idle. So I'm not worried about that issue. So you never thought about that.
But there was an incline endurance where kind of close to the end, we had 4 cones kind of deal.
Yeah.
I almost saw at one point that use that kind of.
Is that yeah.
Yeah, and just kind of comparing if we were to get rid of like if we were to say keep the same final drive ratio and just try eliminating second gear, this kind of table just shows how if our power band between 45 and 9800, if we use 3.4 on an endurance without first gear, our lowest RPM would be around 4300, and with this increase we'd be our minimum would be above our power range, so we'd be within that value throughout the whole course. And going more into structurability, so as I was saying, that little red circle is what the mount that we used last year, and I think that was causing just a huge moment on the mount and bolt. And so I'm kind of switching to using this bearing block where it's more 2 pieces. So this benefits us in 2 ways. Where for serviceability, if we need it in any case, if we don't have to take off the whole bearing block, we would just unbolt these 4 spots. And for tensioning, you would just untension or loosen the 4 bolts and just slip shims into there. And also for manufacturability, we'd only have to machine the bearing housings that are like outboard, and the 2 bigger pieces, I'd just be able to water jet them. So that makes manufacturing a lot easier.
What's that?
You sure you're able to water jet this?
These pieces?
You're going to have a critical interface with your bearing blocks. It's going to be presumably in the direction of the water jet, so you're going to have to mill those.
Oh yeah, I'd be facing them also. No.
Are you worried about mounting to the chassis at a point that's not a node, considering there's a considerable amount of load going through that?
I calculated those, so with this geometry, I'll kind of get into the forces with this one. It was showing how, with this geometry, since the nodes are a little farther, or the forces where they're acting, that load on my mount A decreases a lot more. Yeah. So
you increase the load and decrease the load.
Mm-hmm. Yeah. So this way, since those mounts on the chassis will also be in double shear, it'll decrease load and be in double shear, so it'll kind of just make sure that nothing will yield.
So what 2 thickness do you have there for the top mount?
So the thickness on the top line would be 49 out.
I would be more worried about the tube actually having issues rather than the actual mounting itself. Do you see what I'm saying?
Mm-hmm.
So yeah, I don't like double shear wouldn't necessarily help that, but you have a really good point with increasing the moment. So.
Mm-hmm. Yeah, I'll make sure to talk with her and just get like an actual factory safety for that.
Yeah, keep in mind that ours did, the loads are different here, obviously.
Mm-hmm.
Obviously, the biggest load would be 8. Yeah, just make sure that your mounts are thick enough there.
I think when it yielded from your, was the bottom mount?
It was bottom mount. It
Bottom.
was, it was 45. And then we beefed it up to 35. Oh, dude.
Okay, I guess I'll do the math, but I think the top mounts, I looked at it also, those are closer to the mounts because that number is a little shorter also. So I'll still do the math just to verify it. Yeah.
Is that bottom bolt going all the way through the engine?
Yes.
So you're gonna have to remove that bolt to get this assembly out, right?
At point B.
That's why you have the brackets for the.
Yeah. So if we want to take it off, this piece could just stay on the engine the whole time.
I see, okay.
So then if we need to do any maintenance, we can just unbolt right here, and then you take that piece off.
So actually, why are you gonna bolt it off?
What's that?
So you bolt it, are you having the threads on the, is it gonna be a whole bolt through the whole assembly?
Yeah, I was just gonna do
Okay.
2 or 3 bolts.
Okay.
Getting a wrench in there might be hard. Just a quick comment.
I put like a CAD and a wrench did fit. So it's just going into FEA. I didn't do the deformation, so like you were saying earlier, I'll take them into account too, just to show side by side if the stress isn't enough. But putting the loads in both directions, or both components, and mounting it at the top and bottom has a factor of safety of 2.33. And as for the bearing mount, with all the reactionary forces, it comes up to a factor of safety of 2.81. And although my factors of safety are high, I'm looking more at my weight reduction. We had a 10% decrease, but I was able to decrease from 4 pounds to about 2 pounds this year, just because they had a steel tensioning last year, and I'm using all aluminum this year with the shipping method.
What aluminum is that? What aluminum are you using?
7075 T73. And after systems integration, so for most of the bolt holes, I'll be using M10 bolts. This is just constrained by the engine mounts. I'll be using, for the shims, I'll be using steel water jetted shims. And just to make sure that these don't slip out during, like from vibration or anything, I'll put like 2 holes in them and just implement something where we could put safety wire in so they don't back out. As for manufacturing plan, the axles will be purchased from RCB. We're using the same Drexler differential, the 520 chain, and I'll be manufacturing the sprocket mount, and the 2 components of the bearing blocks. And as for jigs, just the sprocket jig, sprocket mount jig, and potentially I might need fixtures for the other 2 components also. Just going more in depth, so I'll be water jetting the bearing block mounts, and then I'll create a fixture just to drill the holes and finish off the surfaces so they lay flat. Creating a jig for the bearing housing, machining the bore out, water jetting the sprocket profile and then chamfering it, and creating a jig for the sprocket mount and then machining that. After pressing all the bearings in, assemble the components to the engine and chassis, and my system will be assembled. As for project risk, so as I was saying before, how the mount on the engine yielded, so to mitigate this, I want to just avoid single shear mounting, and I also altered the geometry just so the loads are more distributed. As for the shims vibrating loose, just designing a locking mechanism, like safety wire, or possibly looking at other things. And as for sprocket alignment, just making sure that the surfaces are machine flat so there's no misalignment. Any questions? Okay, pass it off to propulsion now.
So Brian. Fuck you. You think you're so funny.
You can change it, but I need to look at it. Yeah. Yes, ma'am.
I would take a look into choke flow. I can know if there's better explanation why you choke flow.
Right, I went and I talked to a few professors. We're not choking, but we are running into a 0.4 Mach number, so we have a little bit of compressible. And yes, we are not choked per se, so that's why I want to say we're empirically going to test if we gain a little bit more. And so I talked to Sal about this, and we can't come out to like a way that I can solve it analytically. So it's going to be empirical testing at this point.
Are you guys still tuning with semi-sequential, or are you using the full sync?
No, speed density, semi-sequential, so weighted spark. Yeah.
Okay.
Ryan does have full sync?
No, I'll talk about that. I'll talk about that when I go.
We talked about this. Okay, next slide. All right. So I have to show you my integration. So this is Explorer view. So how the intake is connected to the engine is by 2 rubber gaskets using 4 1032 bolts. And we're going to have a partial blocking plate because it doesn't bolt directly into the engine. So I don't have it modeled, but it bolts on the side of the engine using the motor mounts. Epoxy will be, if you know about the intake, the epoxy will be, it will be epoxy to the plenum flange and all the carbon fiber pieces, except for the coupler, where the red and the orange is. We're gonna have a, I don't know if you want to, Wiggins clamp coupler. Okay, there you go. And all the aluminum parts are gonna be welded together. And as well as the field rails can be welded onto the runners.
Question.
Yeah.
Are you gonna design some supports to weld onto the?
Yes. It's gonna be, there's gonna be a support on the rope hoop to the restrictor to hold the throttle body up. Yeah. Okay. Oh, this is my manufacturing plan. It's very straightforward. We're gonna order stock. I'm gonna take my time to CAD up the molds, male molds and female molds. Female molds for the plenum and the elbow and male mold for the restrictor. And then I'm gonna order aluminum piping that's standard. It's 1.5 OD and 1.402 ID. And then we're gonna cut it and bend it and I'm gonna weld it together. And very straightforward. Next one.
Question.
Yeah.
Have you manufactured with composites, or have you talked with your composites team about manufacturing those?
Yes.
Okay, you have a plane weave listed up there.
Yeah.
And that, just based on your geometry, that looks like it's gonna be very difficult to lay out, because plane weave is a very stiff weave, so it's gonna be kind of difficult to get over those really, really large reach height.
Is it, I had a discussion with Luis last week. Is it really, I know we have a few options, but I don't know myself. Is it really that, is it hard to bend? I'm just.
Try it and see for yourself.
Okay, yeah, I'll try it. We'll
It's-
make a few of them and see what we see.
From my experience, when we made the 2017 chassis out of it, it was very difficult to get into like tri pockets. So I would recommend either like a 12 or like an 8 harness. That's easier to do.
We talked about that, we wanted to do 12. Are we out of 12?
We have 8 harness. I would also.
We're out of 12.
I would also recommend looking into the Axiom materials we have. Those ones are fairly fresh and pretty easy to work.
I know last year we used 12 and I wanted to use it too, but yeah, it's okay. We'll talk about this more.
And then another thing, so that T300 is an autoclave only epoxy.
Now
And
that
you guys
you
were getting
said
dry
that,
spots with it.
Right.
And I know you guys want that to be like sealed.
Okay.
So Axiom is oven, so I would look into that.
Just make sure you're fully sealing that, because if you get, if you get a porous laminate, you're gonna leak like crazy.
Okay. Thank you for your input. Okay, next one. Yeah, go for it.
Have you done any fluid analysis on the spans at all?
No, I'm wanting to do it this week.
Okay. Yeah.
I wanted to put it into answers and have flow analysis. And if I have some really big separation or expansion, then I'll change the design.
Make sure you're getting even flow in each cylinder. If you don't, you'll see house temperatures vary from
Okay, sounds good. Thank you. Okay. We'll talk about that after. Go for it. Next one. So we have, one of the risks is we have a little backfire because of wasted spark semi-sequential. So I'm gonna continue to put the pressure relief valve. I didn't model it because I forgot. But it's gonna be sitting on the backside of the intake. And it will stay within surface envelope. Bond failure is also a risk, so we're gonna try to use different epoxy this year, not judge it well. Nate suggested 93, 94, so we'll give it a try. Air leaks, same, we'll do epoxy. I didn't put it up here, but we got sponsored to 3D print the intake, so I'm gonna 3D print another one and have it as backup and see if if it weighs less and it works just as great, then we'll use it. So that's my backup plan. What's the material? The material is I know it's 30% carbon and the rest plastic, and I know they use it in their intake system. And who my sponsor is Simo Garage, and he used to go to Cal Poly Pomona, and he prints their 3D. I mean, he 3D prints their intake as well. So I'm sure it will work. But I have to reach out to him, and he'll give me the material specs, and then I'll.
It's probably the market forge machine.
Okay.
They have like this composite material, it's called onyx, and you can mix it with carbon fiber as well, or fiberglass. That's probably what it goes.
Okay. Yeah. Next is gonna be Hui.
Alright, so I'm designing the exhaust system this year, and I will be designing the system to meet or exceed 68.9 peak horsepower by incorporating Helmholtz tuning based on the primaries length and transfer matrix method for the muffler, while reducing the overall system weight by at least 10%. And I'm gonna be designing with the space constraint of the front driver cell and the rear frame, with the length of 1 inch, the width of 16.68 inch, and the height will be 10 inch. And I will go over that in a couple of slides later to show more visual. So for my parameters, I was able to design the primaries to be roughly around 20 inches. The muffler dimension with the inlet to be to have an outer diameter of 2.15 inches, the length of 0.75, the midsection of the muffler have the outer diameter of 4.78 inches, the length of 20 inches, and the outer for the outlet, the outer diameter of 1.5 inch, the length of 9 inches. And these dimensions were modeled from a Hindle muffler that we were able to find in the shop. So those parameters were based on that muffler. And so with these parameters, I integrated with the whole assembly of the car, and I was able to meet with the space constraint, as I said before, and the muffler was able to sit inside the side pod according to the rule. And with that, these parameters were also integrated into Ricardo Wave, which Erwin will go over in his section, but I was able to get the 73.88 peak horsepower out of these parameters.
Question. So how does your exhaust tie in with the intake?
With tuning with the same flow rate, the mass flow rate of the same amount of intake plus fuel is equal to.
Okay. So what's the point in designing? Like, what's the main goal of designing a muffler system?
Muffler?
Yeah. Or your exhaust system. In a fluids perspective. Same goes for intake, so you might want to answer too.
Just
we want to do scavenging, and we want to
exhaust scavenging for better flow.
So when you scavenge, at least like in Helmholtz theory, you target RPM, right?
That's
Yeah.
correct. Our target RPM is 5,500.
No, 8160. If you change it later, it's the same results.
So with
Same
the
results.
exhaust, the goal of your exhaust is to reduce loss at a certain RPM, and that has to work in correlation with your intake. So in your guys' slides, I haven't seen what RPM you guys are trying to tune to, and you guys are saying you want to reach like 68 horsepower.
So
we did had so in our MDR we had our target RPM at 5,500, and with that we run the Ricardo wave with both of our his for runner lane and my primaries with the whole exhaust system, and with various length of both of ours, we saw that the power band for multiple lanes were relatively the same. So that's why we try to pick the shortest length for weight. So and that's why we as far as like RPM wise, we're even though we got the tuning RPM at 8,100, it doesn't change much for our lanes to in like that power band.
So in the beginning of the presentation, I posted a picture of a dyno, multiple plots from Ricardo wave, multiple intake, multiple exhaust configurations that correlate to each other, right? Based on the number of bounces in the intake and exhaust. Ricardo wave showed like the graphs look almost exactly the same. I can show you like after, because it was in the first few slides of like the whole presentation. So with that being said, like camshaft theory, camshaft lift and duration, and also head geometry, I think are the primary like reasons for where your power band is and how your power curve looks. Not so much intake and exhaust lengths. And I think that the Helmholtz theory has more value attached to it than what I've seen from the results.
Right. However, though, yeah, cam timing does play a big factor on your torque curve. But when it's like assume it's constant, your muffler and your intake, when they work together, you can scavenge. You know, you're saying you're scavenging. When they work together, you essentially you pull more out of your engine, and you pull more in and out of your engine at the same specific RPM. So yes, you're constrained, but it helps you to work at that point where you're constrained. So, because I've done empirical testing on the dyno as well, and I've seen how our intake, we aimed for about 5,000, and we saw an actual increase at 5,000 RPM before we tuned it. So,
how much does it increase? For the Ricardo, it's only plus or minus 3 horsepower at various regions.
Right.
Plus or minus 3.
Is that what you noticed?
And
it's not a lot, but when you're restricted, it can actually play.
So I guess the reasoning, when I talk about my slide, they use VE graphs generated to see where I'm actually getting the most flow. That was the reason I went forth, because I don't want to test a bunch of stuff in the dyno later. It's for time, and I can't test it right now because the car's not running right now.
Right.
So
well, regardless, I mean, make sure you guys like express what your goals are as a whole powertrain system and how they correlate with each other.
So yeah, that was stated in the beginning of the presentation.
Okay.
Yeah, that's what I'm trying to say. Yeah.
Okay. Cool.
Yeah.
So more visual, I compare last year design and the current upcoming design, and the primary length of last year was come out to be like about 31 inches, and this year I was able to get it to 20 inches, and because of the dimension of the muffler from last year, this year didn't quite change much, so the weight of both were relatively the same, and as a whole two system, I was able to reduce roughly like 6 pounds, so that gave me about 30% weight saving. Next, this is the CAD model that I was talking about. Like, so my space constraint was between the driver's side and the rear frame. So, and according to the rule, I need to be about 1 inch away from the driver's side, so I was able to meet that space constraint. Yeah, for 1 inch away for a convection system, it just exhausts. So, yeah. Cool. Here's a picture of how I'm going to have the muffler supported by this exhaust hanger, and I will go over that in the next slide for iteration. And that's the front view without the driver's side. whole system will look. Yeah.
Do you know how hot you can get the back of the chassis from your exhaust system?
We did incorporate the temperature in Helmholtz tuning, and the exhaust temperature, it was like, I think, I forgot. I have it in here. Just give me a sec.
If you have the temperature of the exhaust gas in the pipe, when that becomes, take a little bit off, becomes the temperature of the pipe, then you have distance from the pipe to the carbon.
Right.
You understand how much heat is getting to that carbon. Because if you guys get that too hot, you're gonna delaminate the back of the chassis.
Yeah.
Like we have done 100 times before.
Yeah.
You Zergo flex that shit. The Zergo flex stuff.
Yeah, the heat protecting, yes.
What is that called?
No, no, it's not.
Zergo
For the rules,
Tech. Oh, okay. Yeah.
And like the gold foil.
Yeah, the gold foil stuff.
Yeah, I mean, that
Yeah.
helps to reflect some of the heat, but you
Yeah.
also need to understand at the surface of the back of the chassis, how hot are you getting it with your design? And do you need to add any other heat mitigating things to keep the back of the chassis in one piece? So, because it's a really hot system, very close to carbon,
Mhm.
you need to understand what the effect is gonna be, the judge will ask you about that.
Right. I'll look into it, for sure. So for system integration, I'll have the primary mounted to the exhaust head by four 14 mil exhaust nuts that will be fastened to the M8 exhaust studs, two exhaust flange that will be welded to the primary, and so with the two exhaust collar. And the primary will be press fitted to the collector using two exhaust springs, and the collector will be welded to the 90-degree pipes that is mated to the muffler inlet. And that I will be using a V-band clamp that with a nut and bolt mechanism to clamp down the 90-degree pipes to the muffler inlet. I didn't have that model in here, but yeah, it'll essentially be clamping these two points together. And I'll be so the picture before this shows the exhaust hanger, which is the design that I will be going about to support the muffler using a 3/8 inch bolt and 1/4 nuts. An exhaust rubber hanger, I don't have that model, but it's a pretty basic. I think I put the size wrong, but yeah, and also using the exhaust rubber hanger to help support the muffler. For manufacturing plan, I'll be ordering the pipe stock, exhaust collar, and the collector from SPD. And since we're going with the aftermarket muffler, I'll be looking at a used Hendo muffler from eBay or Craigslist for that. And then once the stocks and the parts are in, I'll be cut and weld the piping, then weld the hanger and the exhaust collar, then assemble the whole system. In this plant, the most critical part is packaging the primaries because it needs to line up with the collector and make sure that I was fit between the space constraint. And this is my a visual of it. So once the parts are in, I'll be give myself some time to make a jig, cut the pipes and weld tubes, hanger, and exhaust collar. Then that's gonna be like a really long time for me to get all those completed. And once the primaries are made and mufflers are in, I'll be assembling the system and completed roughly about like beginning of March. That's my goal to get it done. And material selection, the primary will be the stock will be 304 stainless steel, same with the collector, and the aftermarket muffler will be out of either aluminum or stainless steel, based on whatever the material it is. For project risk, there will be 3. The exhaust nut backing out due to vibration. This actually happened last year, And to mitigate that, I will be torqued that down to spec and use high temperature Loctite on the studs. And the second one is the exhaust hanger broke off. This was a problem in the past also. So I will be making the material thicker, just not too crazy, but just a little bit thicker, and reinforce the hanger mount. And lastly is the exhaust primary backing out of the cylinder head and the primaries, and the collector, which then will give us a lean engine. So to mitigate that, I will use a double exhaust springs and weld the collar to the primaries to reduce the chance of it backing out.
One thing, I remember our exhaust hanger broke off prior to. Keep in mind the thickness of the collector as well, because you may thicken up the actual hanger, but the weak point's still going to be there, because our weld actually broke the actual exhaust, because the thickness was too thin.
Yeah.
So if that's the case, I'll try to get the double ones or something.
Yeah. Okay.
Thinner, but you spread the load a little more.
For sure. Yeah.
Last I checked, exhaustics cause a rich rank condition, not a lean condition.
Why?
Wait, what's
Because
up?
you're tricking the O2 sensor, thinking that there's more air. in the exhaust
Open
than
loop.
there actually
We're running
is.
open loop, not closed loop. Yeah.
With that,
Guys,
any more questions?
on the tab, you guys could also do almost like a postman thing where they wrap around it. That way that part is accessible.
Yeah, I was thinking of that too. Yeah, but with that, I'll leave it to Erwin.
No.
Oh.
So
My
I'm
bad.
designing the fuel system, and so by designing the fuel system, provide enough fuel for enduring endurance, prevent fuel starvation, provide the engine with the max fuel volumetric flow rate of 442 G per minute, reaching the goal of 73.88 horsepower. Reduce the weight of the whole fuel system by 10%, and the fuel tank must fit in the firewall dimensions. As you can see, this is my design solution. We decreased the volume from 1.9 gallons from 2019 to 2020 to 1.5 gallons. The weight difference, we gave us a percent savings of 10% when this is a SolidWorks model. And it's very minimal, but it's still it meets the goal. When the fuel tank gets theoretically full, with the fuel pump, everything on the fuel tank, it weighs 16 pounds compared to 20 pounds for 2019, and they gave us a percent savings of 19%.
Sure, it's gallons. Is that liters?
Wait, what?
It's in gallons, but we're measuring in liters. Yeah. Sorry, it's the SAE does in liters, but I'm doing it in America. And then for my ejector mounts, I reduced them in length by 0.4 of an inch. I changed the angle on it so we can have our fuel pretty much straight into the intake valves, close to the intake valves, and have a fuel mixture of our desired lambda of 0.8. Also, the decreasing of the length saved us a little bit of weight, but not too much to mention.
Can I ask how you got those angles?
So just to research, I read papers on how the optimal angle is to have your fuel being sprayed into your intake valve at a 45-degree if you can.
So if you're saying the optimal is at 45, why do you think that previous year's reasoning for putting it at 38 was?
The way the intake was back, and the intake run from back, just went like that. And then this year our intake kind of straight, and then we're able to just mount it right on there.
So you think they just weren't able to?
I don't know if they weren't able to, or no, they just did the research or read, still by read.
Yeah, keep in mind that angle changes a lot depending on your intake geometry. So your flow, it changes with every intake that you have. So whatever paper you may read, you're not actually what your engine is saying, especially since our intake is restricted. So if you have time, I would try to test different angles on the engine to see how it plays a difference. Because fuel angle changes your ionization. I think
Testing, empirical testing?
yes. So probably I put a lot of effort into fuel angle and actual changing your fuel pressure.
Okay.
ask me those questions at the competition, why I met the pressure I ran, why I actually tested schedule.
Okay.
You know, there's a whole Schlieren imagery too that I try to take a look into, but it's a pretty big deal.
The whole what, sorry?
Schlieren imagery.
Oh.
So it allows you to see the changes in density of the fluid or in the air. If you're looking at like a shadow or something, you can actually see it, but that requires your the whole the flow bench, bench set, the flow bench is has a camera set up and whatnot. But there, when you actually the deep into the actual flow rate of your intake and how it affects your applications.
Okay. Oh, and then for my design goal solutions, we came up with I came up with 1.5 gallons, using 91 octane. I used pretty much our results from 2018 and 2019. And in 2019, we wasted 1.3 gallons for endurance, and our fuel tank size is 1.9 gallons. And we came up using Ricardo Wave and Optimum Lab. It gave me numbers through my calculations of 1.5 gallons that we would waste using an average time, which is like the worst case scenario. The weight reduction was, our goal weight reduction was accomplished by having a 23% percentage loss of fuel starvation, using a highly hydromat in our fuel tank, and the fuel flow rate to achieve the goal using Bosch EV14 injectors, and a Walbro GSL inline fuel pump.
Question, is anyone octane approved now for SAE?
Is it what?
Anyone octane?
No, it's still 93, but we just,
Oh,
yeah,
yeah.
it just, yeah, it's, yeah.
And then from system integration, there's image. This year I'm using two fasters, kind of like last year, but made in brackets a little bit bigger for serviceability. We have to remove the fuel tank. I made a little bit higher, so your fingers are hanging in there. And then we have to put the PG under and the other data. And then the rear of the fuel tank, I'm using 2 pins. So pretty much when you mount it on, it'll be where you desire it to.
Question, how does that integrate with your exhaust?
With my exhaust?
Yeah, how does that integrate with the exhaust?
As in, does that? Oh, like as in it's. I don't have the image of it, but it fits.
Like is it closed? Is it?
It's just not close at all. It's pretty. It's have pretty good distance away from it.
Do you have the option of putting it from the other side, your lower neck?
On the other side of the field?
Yeah, just further away from the exhaust. If you want to keep your fuel as cold as possible,
Yeah.
the colder it is, the better.
I think on that side it's probably actually closer because the bands go on that side. But I could think of check that out.
I'm guessing you're on water jet, just a few pieces together.
Yeah.
As the bottom piece gonna include those 2 tabs.
What's that?
That bottom base gonna include those 2 tabs.
This bottom page?
The bottom piece of the tank, the bottom piece of that tank on the top right.
On the right picture. That's your left. Yeah.
Those 2 tabs taken out, is that gonna be part of the bottom piece?
Yeah, it is. Yeah. So we want to just complete. And then this system integration with the field, injector fuel amounts and intake is excuse me here. And then they'll be welded onto the, if it's 3D printed, we'll have it 3D printed complete with the intake system. If it's, we make it aluminum, we'll go welding it together.
Are you spraying right at the valve?
From the image that we have from the SolidWorks model, from the XIII, it seems like we are. We just ran an analysis on our CFD on it. And from a manufacturing plant, it's purchasing what will be like throughout going to break, purchasing aluminum stock, water jet, and then machine and injector mounts, and then the fabricate. And then my goal is to be complete before March, beginning of March. And then project risk that I might run into is an assisted fuel delivery to the engine, which could mean will be mitigated by having the correct injectors, correct fuel pump, and also we can have a fuel injector failure or fuel pump failure, and I'll mitigate that by having an extra set of fuel injectors and a fuel pump.
just in case. And then fuel lines and fuel fittings and failure, we're gonna be using BMRs.
Usually these risks of failure things are looking for a design decision to mitigate that risk so that it doesn't happen. So your second line there of, well, the fuel injectors could fail, so carry extras is not a good thing to put up there.
Okay.
If you have a concern of your injectors failing, please understand why you're concerned about them failing. Are you over duty cycling them or whatever like that?
I am under the duty cycle, 80% duty cycle. It's just, I mean, it could happen.
Then by design, your injectors should be okay. So that's just a component failure that happens in things all the time, but you would design within the parameters of that component so you're not expecting a failure.
Okay.
These kind of failure analysis, like you're looking at what in my design could have gone wrong that I should have designed to prevent, not will the ship run. So you may want to redo this one.
Okay. Any other questions? Okay, jump through one.
So before I start, I'm the last person to present. So after this, enjoy your Saturday nights. Thank you guys for staying. So yeah, new calibrations this year. No. No. I wanted to present. Huh? Why?
We have to present the cars as a whole.
Oh yeah, I forgot. Never mind. I'm not the last person. I forgot about that. Joseph, you walked in here. I'm like, who the hell is that? I didn't recognize it. I honestly
you shave your beard while you sleep.
I didn't recognize you. I swear to God. Hey, you fucking up my presentation, dog.
Whoa, it's really dark.
I wasn't nervous.
That's fine, yeah. I forgot about that. I'll say it. What I've noticed from just empirical testing in parking lot, run after run, getting back feedback, I've noticed 120, 175% Excel fuel enrichment, and then yeah, cutting 10 to 70% fuel for deceleration. I'm not going to cut any more than that because I've noticed when the driver sets like on the gas, there's a hesitation. Yes, the fuel's not in there already. So that's just empirical testing over and over again. And with startup time, the startup compensation now is dialed in to the point where it's hot or cold and starts to ride up. It's been like 3 or 4 cranks. And I have achieved the goal of under 2 seconds consistently. Yeah, took out shoot out the whole day. It was like that. So it was nice. Stall recovery, it's a big thing because endurance last year, we lost like 6-7 seconds just after the driver hit a cone or stalled, whatever, spun out. Because it was wet. Yeah. But even at 85, it's still out shootout. 85 is dialed in. So I'm saying I'm going to go back to 91, but we're not limited. So it should be even easier to dial it in. Did I answer? You asked. Oh yeah, I did answer that question.
So
Okay.
you're gonna answer it later.
Which one did I forgot which one
Why you're doing super rich and why how that's gonna get you more points.
Oh, okay, yeah. So with the 0.8 lambda versus a 1.0, those are the two extremes. I'm not going to run any leaner than 1.0, and I'm not going to run any richer than 0.8. So those are the two extremes. Given the same amount of time for endurance, right? So this is disregarding, from what I see in driver feedback, that running a bit richer and having a nice calibrated pace map through those lambdas make the car a lot faster. This is disregarding that fact. Same time for endurance. I used 0.2 gallons more fuel if I use the richest lambda for across the board than the leanest lambda, 0.2 gallons. That correlated like 20 something points for fuel efficiency. However, like I said, that's with the same exact time for endurance. Last year, we didn't even get any points for endurance for field efficiency because we were so slow. I'm going forth with driver throttle response and having the driver focus on the track and not the car. This past year, we were for a comp we ran a closed loop, and with PE3 the response times that closed loop system is not very fast. It's the fastest you can do is 50 milliseconds. And talking to Jared and even them at SEMA, they're saying their closed loop system is meant for more, I guess, the cruiser type vehicles where your TPS rate of changes are not as high as what we see. So it doesn't react as fast as what we want it to do. So we're going to just stick with open loop calibration. And I trust my base map because I've done steady state on every single cell on it, and I've got it dialed in to 0.85 targeted and the variance of 0.02. So I trust that, and the drivers seem to really like it. And I don't know how much faster we could be until we build a car and like I can run a test to see 1.0 lambda versus 0.85. I've done it, but just from talking to them, talking to previous years, they would much prefer the car to be drivable rather than penny pinching on fuel to save those points. I don't think the trade-off is worth it, but I did calculate the trade-off is 20 points, 20 something points if we.
So how much faster do you get to get endurance to make up 20 points?
That's what I'm saying. I don't know how much, because it's like, no, because in fuel efficiency it's based on endurance time too.
Right.
So it's
right.
like,
so
it's,
okay, let's ignore endurance. Let's
yeah.
say it's autocross, right? Autocross, you're gonna go faster too.
Well, autocross, it doesn't make a difference because they're not
But
calculated.
he's saying how much more points you're going to get from a better handling car.
So yeah, autocross, XIII, skid pad, those three events are all, I feel that we're gonna get a lot more, like I don't know the exact amount, because I can't give you a time for how much faster throttle response will give you in terms of lap time, just from driver feedback, and just saying that it's much more controllable. They're gonna actually focus on the track and not.
The way I would have asked that, you have two equations online that tells you how the points are done.
Yeah.
So you're right, endurance matters for fuel efficiency and the time, so you can't really go there. But you could go to autocross and say, okay, how much faster do you have to be in autocross to make up 20 points? Yeah, last year's best team has.
So the problem with that, I'm gonna get the same horsepower, almost the same horsepower ratings. And those equations, like from talking to vehicle dynamics, that their inputs are the same regardless of lambda. This is about transient throttle, not base map.
So a good example is skid pad. We have early in the system I showed how in skid pad the car was a lot more capable of what it was, and we were having a lot of issues with that. One of the large reasons that we weren't having potentially as fast a time as we could was because of that throttle response. So we were having issues with every time the driver put on the gas, it just transient, so throttle was not there, and so the driver couldn't predict the car and therefore couldn't get the best time of skid pad that he could.
Yeah, so that's what I know what you're trying to say. I could have calculated, but the course, like I can run Ricardo. Ricardo uses fuel to air, not air to fuel. So it's whatever, same thing. I can just do the inverse. I inputted 1.0 and then 0.8, the two extremes. It's like 1 horsepower difference, 2 horsepower difference. That does not account for throttle response though. That just shows peak. So there's a base map you calibrate, base ignition timing, base fuel map, and then you do transient throttle. That stuff is way more difficult and very important. That's like the final piece of the puzzle to get a good running car. What?
Well, keep in mind though that skid pad and endurance are completely different in terms of how you're driving. When you're doing skid pad, the slightest position, slightest movement of the throttle, you'll spin out.
Yeah.
So, but that's why you have multiple tuning maps.
So I'm trying to eliminate that. I'm trying to just use one map for. I don't like that idea of multiple. Then drivers have to focus on multiple ways of driving rather than just sticking to one and fine tuning their way of driving.
My second point though is that it really doesn't make that much of a difference. Because when I did my tune, I had values around 13.5, 13.7 on throttle in endurance, and it's not like you're plug-in or it's still pretty smooth. You shouldn't have to worry too much about throttle response at that high of a.
So yeah, 0.85 lambda is close to like a 13. So it's
like very low 13, but I'm saying you could push it a little further.
Yeah.
Instead of like 13.1, you could push 13.5, 13.7. Keep in mind, like your exhaust temperatures will be the biggest deciding factor on what's safe. 800, I think is good.
Yeah, and then above that, it's
going too high.
Yeah.
Your target time, but
Yeah, I don't think you could.
This is just based on the feedback I've got from my drivers, and then our main driver Brian Strubert's an actual like race car driver, so like his input means a lot to me. So when he tells me he'd rather just stick to one thing, just have him focus and train the rest, that to me matters more than creating multiple maps. And if I can just create one map that's good and responsive, like how the OEMs do it, like I'm trying to just follow OEM calibration, like smooth. All the car starts up when you want it to start, shuts off when you want it to, and just everything OEM. That's like my ideology. Wait, did you have your hand up, Alex?
Yeah, but Brian got some of it, so I'm trying to come up with my next one.
trying to reload.
Out of curiosity, how many drivers do you guys have?
We have one main guy and then like two so far, so 3 total right now. We're still working on our 4th.
Are you guys gonna do like one driver per event?
I don't know that. I can't answer that
All of our
question right
drivers
now.
cross-trained. Because we're.
Okay, sure, like in case something happens, but before the competition,
There should be a special. There'd be a specialty. Like each one will have like a specialty.
We will have one person who's naturally faster at all these things, but we also don't want a situation where your best driver is always training for whatever, and then you have, well, what about your guy who's the 4th fastest, and he still has to do autocross or whatever.
You should be doing every scenario when you're training, and if you're doing
That's what I'm
skid
saying.
pad that day, you should have your skid pad driver driving, not your autocross driver driving.
No, yeah, that'd be, like we know. Yeah.
Okay.
Yeah.
And to sum it all, I guess, if you're tuning for power response, that's a good idea. I respect that. Just if it's in terms of fuel efficiency, it's not like the best design solution.
Yeah, I 100% agree with you. I am taking a hit. I just need to, if you give me more time, I'm gonna try to calculate theoretical lap times. What I could do is parking lot test when the car is actually built again. I'll put the engine back together. Parking lot test is 1.0, and then no, dude. All right, I'll keep talking. 1.0 versus 0.8 lambda, whatever. I could get an autocross lap, and then find the percent difference. The percent difference is the same no matter what length of track you have. So I can do that and get back with you. Cause that is in the works. That's hopefully by January, February I can do it.
Cool.
I want to prove it for designer comp, not for this because the car's not working now. All right. So manufacturing plan. So it's pretty important for PE3 to have a nice laptop. So first step is to buy a laptop. Second, make sure your battery's charged. Third is to open the laptop. Then you gotta make sure you got the PE3 software on there. And Sal likes to make fun of car guys because he always says you car guys read Hot Rod magazine and LS Swap Facebook forums and don't know any engineering. So that's just, it's important though. A lot of LS Swap forums give you a lot of good insight for calibration, I think. And you gotta plug in the cable to the laptop and then plug in the cable to the car. You gotta turn on the master key, then turn on the ECU. Then you gotta connect the P3 to the ECU, and then you gotta push buttons on the keyboard. Stuff happens, and then it makes the car go really fast. Next slide. Project risk. Next, project risk. Wait, you didn't change the title of my thing, Eric. The fuck? Example, project risk radio. All right, never mind. So, unresponsive throttle. So yeah, that's just a risk I see decreasing our overall lap times. That's just either throttle, fuel mapping, accelerate, decel. Intake backfire. This is like our plenum. Sometimes it blows flames out of it on the startups. So I dialed in the startup fuel conversation, and SoCal shoot out the whole day. It only happened twice out of like an 8-hour run day. So I think that's pretty good. And then I've retarded the ignition time so hopefully that it won't combust near the intake valve later in the stroke. So it won't go back inside the intake.
That's the Oasis part too.
Yeah, Oasis part.
Also, going way past MVP timing, so you can also do that.
Yeah, exactly. Yeah, I 100% agree. Didn't put it on here with Oasis Spark. There is a way we can incorporate a Hall effect sensor in cylinder head. Just drill a hole in there, put a steel bolt on the cam, let it spin, and Hall effect on it. Working on that, and the only issue I have right now is just how much space I have between the wall of the cam sprocket and the valve cover. That's in the works, so hopefully I can run. I don't have to do that anymore. But I got Oasis Spark and semi-switch dialed in now, so I don't know. We'll see. That's it if I have time. Engine overheating. This is only if it's like a really, really, really hot day and we're driving nonstop, like driver training days. Like airport days and like a Ford and airport, like 98-degree ambient temp, 140 track temps, constant running. I had to run it a teeny, I just multiplied the whole map like 10% fuel just to keep, and I did notice cool temps drop and stayed within my running range, under 210. And exhaust after fire, so not backfire, after fire, just combusting after, okay? Taking away a bit more fuel in decel and advancing ignition timing in off throttle areas. That's just the way I'm gonna get rid of that, and that's been gone since then. I think that's it for calibrations. Check the next slide. Oh wait, no, is that what you want to do? Okay. All right. We're powertrain's done. So yeah, we have one more important slide to show you guys.
All right, so this is the number that we've all been waiting for. 467 pounds is our final designed weight. So again, this is kind of looking at our goal is actually 472, and we actually got really, that's a pretty good number, 467. So maybe we should just re-go over the last slides, but yeah. So the last year's weight, 500 pounds. Our target goal was 472, and when you add up all the parts that you just saw from everyone else, the car comes out to 467 pounds. So yeah, it's pretty good. And now for the full car. Bam.
Wow.
So yep, that's our car. This is actually the first time like a lot of you guys have seen that probably, right? Not even from the team. So yeah, that's our presentation. I guess now so I think one thing I know, just out of curiosity, for the alumni, a lot of you guys came late. Do you want us to go over like the top? I can go over the top level stuff really quick. No? Okay. Cool. Yeah, I think. Thank you for coming. We guys can break off, talk to your.
We're exhausted. Don't
Yeah,
worry
yeah.
about it.
I know there's not a hole in there now.
Yeah.
What the fuck?
I know.
If you just leave it exhaust, it makes a hole, okay? It's fine.
Yeah.
Turn the car on. Are those the same side of the Oh, yeah. They're the same side, okay.
So yeah, if you want to notice, there's insane amount of detail. I had one thing I really wanted to push for this year was a legit full car assembly. So yes.
Are the wheels on the other side?
Yes, they are.
There's not.
So yeah, I think one thing we want to just work on this year is an integration. That's what this whole presentation was really all about, was to see how all our systems can integrate. How are they integrated? Where they fit in the car, the likes. So one thing we took this year is we pushed it as far as we could by modeling everything. So all the nuts, the transponder, roll bar padding, RFID. There's actually a fuel filler cap down there, cotter pins. And the list goes on and on. But yeah, that's kind of something that we tried out this year. It's another view from up top.
Who the hell is gonna build that chassis over there?
What's that?
Build a hard thing.
That's post-processing.
It better be.
Yeah, we're just gonna lay that one up.
Yeah, so thank you for coming, everyone.
Wait.
Oh,
One
okay.
quick question on the chassis. Why is there a chamfer, not a big radius?
Get the fuck out of here.
Really?
Get the fuck out of here. You came the last minute, okay?
Was there a good answer to it?
There was I don't know, man.
I could talk with you about that.
He was here
I'll talk to you about that right now.
Wait, David, you had a question? To model the wheel? Oh, well. Oh, Jesus Christ. In case you didn't know, David and I spent 6 hours looking at drawing and making a circle pretty much. So. It's pretty much a glorified circle, but hey, it's a good looking circle. So, yeah, so I think now's a good time if you guys have questions. Oh yeah, any questions? What's that? Oh, it's the Fado driver. I think it's the torture driver. I think actually in our this is like a six. This is the
95th model, and then to get like a similar weight to a human, I found the density of a human is similar to natural rubber. So I threw him into natural rubber and he's about 200 pounds.
Why didn't you just look up how heavy do I get on the
I don't know. Well, I wanted to take a selection on the guy.
No wonder why is 185 pounds.
Are you guys making that helmet? For the grab gun?
Grab gun.
Grab gun. Are you guys making a stencil for the roll bar test?
Yeah.
Yeah, it passes tech.
Oh, so they updated that. Where's the front wall? In the 2020.
Oh, yeah, no shit, where is it in the chassis? Like, where's the front back? Are you passing that rule?
Oh, we
did the Motec brings it up a little bit, so.
No, in the,
Yeah.
yeah, we ran that beforehand. We have a model with Roman in there, and we checked that.
Yeah, legally this car
Yeah,
passes.
before we feel like.
Where's the top hat?
But yeah, any other questions, concerns? I think.
Oh.
Okay.
No, we're done.
Yeah, that's pretty cool. We actually managed to do a design review, kind of, and
20 minutes in, or 15 minutes in.
so thanks. All right. Oh, thank you, everyone. Thank you for coming. We'll stick around, talk to your people, and socialize. I guess.
So, one thing you guys gotta do first, I understand there's probably a